This meeting is being recorded.
Yeah. Hi, and welcome back to the second day of CARDIS. Today we will start out with a technical session on secure implementations. It is an online session, so let's see if we are connected to the online chair. Colin, can you hear us already, or?
I can. Can you hear me okay?
We'll have 4 presentations.
Thomas, can you hear us?
Hi. Yes, I can hear you. Hi, Florian.
Okay.
Hi,
Yes,
Colin.
Colin also just said hi.
So you can see us as well. So awesome. All right. So the connection seems to be there. That's awesome. Yeah. So we will have 4 presentations, and Colin, you will be chairing the session, right? Can you hear us?
Yeah, I can hear you fine. Is my audio coming through?
Yes, it's perfect. So good morning for you. It's quite early.
Yeah, 6:30 here, so
Okay.
not probably as bad as other people have it, but yeah, it's too bad. I can see the room there. That looks really nice. I very much miss being in person, so it's kind of extra alluring with this view of it all.
Yeah, exactly. Say hi. Nice.
Yeah, so I guess, am I okay to take over now?
Yeah, sure. Please go ahead. Yeah.
Yeah, so thanks very much. So hopefully everyone enjoyed the social event. As I say, I really do miss seeing everyone in person. So hopefully in the next year. So in this session, however, we do have a number of online presentations about secure implementation. So as in the previous one, if you weren't at the previous online session, these are shorter presentations, and there's a full presentation linked online, as well as, of course, the paper being online. But if you're interested in the presentation, in the short summary one given here, you can see the full-length presentation as well. I'll be moderating questions that are asked on Mattermost, so if you're attending virtually, please feel free to put a question in there, and you put one in anytime. I'll give it to the paper during the presentation, or if there's questions, of course, at the event, please interface between the virtual sessions here, and you can pull us in to ask the questions there. So with that, we'll kick off, I think, and start with the first presentation of the session, Fuzz Key Comparing Fuzzy Cryptographic Primitives on Resource-Constrained Devices. And Mo Zhang, I believe, is ready to go here. So Mo, I'll let you introduce this and take it away.
Yeah, perfect. Can you hear me?
Yes, we can hear you great.
Yeah, okay. So hello everyone. My name is Mo Zhang. I'm a PhD student of University of Birmingham and University of Melbourne. Today, I'd like to give a short introduction of our paper, Fuzzy Key Comparing Fuzzy Cryptographic Primitives on Resource-Constrained Devices. So first, the implantable medical devices, which are IMDs in short, and wearables, are extensively used nowadays. These devices commonly rely on a wireless interface to communicate with each other or with external devices. This can bring convenience to the users. However, this also poses new security threats. For example, if an adversary can alter the commands sent from a programmed device to a patient's pacemaker, the patient's life can be at stake. Sorry. It's necessary to bootstrap a trust with these devices to protect wireless communication. However, this is very difficult because these devices are highly resource constrained. So first, these devices generally have limited computational power and memory. Second, they also have very limited battery capacity. In particular, most IMDs are operated by a non-rechargeable and non-replaceable battery that typically lasts for years. And once the battery is drained, the IMD is replaced through a surgery that can pose risk to patients. And similarly, the wearables typically contain very small batteries, such as button cells. Third, they often do not have any physically accessible input-output interfaces, for example, a keyboard or a screen. And fourth, the network connections with these devices are not always static. For example, in an emergency, a doctor may use a totally new programmer device to connect with the patient's IMD, and this process can be vital to the patient. Unfortunately, many medical and wearable devices available on the market currently lack security mechanisms and are vulnerable to different types of attacks. To address this problem, researchers have proposed to use random human physiological signal, which is PS in short, for key establishment between two body area devices that do not have any prior trust relationship. The principle is that two devices can agree on a key by independently and synchronously taking a measurement of a given user's PS, for example, the heart rate. Here, we want to note that the PS is different from biometrics, for example, fingerprint, because PS is required to vary over time, but biometrics is to some extent invariant. The main problem of this solution is that the measurements of the two devices are always not identical, but they are at best rather similar due to inherent noise introduced by the measuring process. The solution is to use the fuzzy cryptographic primitives, which allow two devices to agree on a key from several simultaneous and noisy measurements of the same signal. The most commonly used fuzzy primitives used by the prior PS-based key exchange protocols include the fuzzy commitment, fuzzy vote, and fuzzy extractor. I won't describe each of them in detail here because of the time limit, and I recommend you read our paper or watch our video for more details. The security of fuzzy primitives has been studied extensively in the past. However, it still remains unclear if it's feasible to use the fuzzy primitives on resource-constrained devices such as an IMD. Besides, it's valuable to know which ones are the most suited for the PS-based key establishment. And for our work, we want to address these gaps. We implement PS-based 128-bit key establishment using 6 fuzzy primitives, including the fuzzy commitment, fuzzy vote, and 4 constructions of the fuzzy extractor. We provide open source codes under MIT license. Besides, we fully evaluate and compare the fuzzy primitives on resource-constrained devices. We also make constant time optimizations on the most efficient variants and test the effect as well. Moreover, we study how parameter selection of the fuzzy primitives affects the performance. For our design decisions or parameter selections or implementation details, I'd invite you to watch our video or read our paper. Here we provide an example, so we show the most efficient variants of the fuzzy primitives in both Hamming and set metric under different mismatch rate thresholds of a PS. The energy consumption values are measured on an MSP430 development board, which is a representative low-power microcontroller, which is similar to the ones used in commercial IMDs or wearables. We observe that the energy consumption of these variants is comparable with curve 25519, which is one of the most efficient elliptic curve-based key exchange schemes for embedded systems. We further make constant time optimizations on these variants. For example, this figure shows that we replace a conditional branch with a Boolean operator to make it constant time. We have verified that our optimizations reduce timing leakage below the statistical significance threshold while only minimally affecting the energy cost. So overall, we demonstrate that the PS-based key exchange methods using fuzzy primitives are feasible for resource-constrained devices such as an IMD or wearable. And besides, we recommend to use syndrome and pin sketch fuzzy extractors in Hamming and set metric spaces respectively, instead of the fuzzy commitment and fuzzy vote, which were frequently used in previous PS-based key exchange protocols. In general, our work serves as a reference when applying the fuzzy primitives for body area networks and medical devices. And we believe that our work is also valuable for other use cases such as biometrics or PUFs. Thank you so much for listening, and I'd like to answer any questions from you.
Thank you very much. That was very interesting. Applause here. In Lubec's side, is there any questions from the audience?
Currently, there are none.
Certainly. Okay, so I had a question, two things. I think for many of us, this sort of psychological signal, usage is newer, not being in biomedical. The first question I think relevant, everyone at CARDIS and these types of events is going to think side channel and those types of things. So how close would you have to be? And even if you didn't do the test, would you feel, if someone were to steal the key off my body? Is this like a very like they would need a wrist strap? How intensely do they have to measure these signals?
I think firstly, one of the requirements for this method is that the physiological signal must be selected carefully, and the physiological signal itself should satisfy certain like security properties. Like we can only let a physiological signal to be measured when we attach a device on the patient's body or on the user's body, and it cannot be attained if the adversary is in a remote position, something like this. So, uh, uh, and another regarding the constant time attacks, and our team think that because we make a core assumption in our model, which is the adversary cannot make physical touch with the patient. Otherwise, he can make much more serious impact on the patient. So, according to this assumption, we think that it's only possible for an adversary to make a timing attack on the protocol, and which is why we also make constant time implementations for our work.
No, that makes sense. Were there other questions from the physical? You
Nope.
not? I'll continue. The other question I had then, you mentioned in the paper about the curve 25519, the power consumption was similar. How did resources like code size, out of interest, compare between the two?
Sorry, could you repeat that again?
Sorry, the curve 25519 comparison you did.
Yeah.
How did like the code size of that implementation compare to what you did, if you remember?
Actually, we didn't implement curve 25519 by ourselves, but we used the prior data of some prior works like that they implement this one efficiently on the same hardware setup that we are using in our paper, and that's why we compare our energy performance with theirs directly, and we find that they are very similar with each other.
Got it. Okay. Yeah. No, I wondered because the your device, I think you had like 2K of RAM or something, so it's quite constrained. So, I also
Yes,
wondered there might be
exactly.
advantages there too for your work.
Yeah,
Great.
exactly.
I don't see any questions on the chat. Let me check again. No questions on the chat. Last call for in-person questions, I think.
Yeah, no, there are none.
All right. Well, thank you very much. Yeah, very interesting work, as I said, Mo. So appreciate you coming virtually, like myself, to this. And with that, we'll move on to the next virtual presentation, Under the Dome, Preventing Hardware Timing Information Leakage. And I believe Matthew is with us.
Yes, I'm here.
Perfect. So we can hear you fine. So I'll let you share and take it away.
Okay, is it good for you?
Yep, it's looking good.
Okay. So hello everybody. My name is Mathieu Escoutelou and I'm a third year PhD student at the INRIA Rennes in France. So during this short presentation, we talk about our approach to prevent timing information leakage from the processor microarchitecture. So during many decades, optimization have been done on processor to try to improve their performances. So new mechanisms have been added to try to focus on some aspect of the execution to finally try to increase the number of instructions executed during a short amount of time. And during this time, designers have only focused on performance, and they completely neglected the other aspects like security, for example. And this leads to the current situation where new weaknesses are regularly discovered in the whole microarchitecture, And finally, a lot of different mechanisms can be exploited to try to leak some information. At the heart of most of this leakage, we have a common principle that we call microarchitectural sharing. So this mechanism allows to different software processes to share some data or resources at the hardware level. So we distinguish two kinds of sharing: the spatial sharing, when these different processes can access simultaneously a data or a resource, and we have temporal sharing when they access them at different moments. And the issue with current implementation of sharing is that other information are also shared, like timing information. And finally, an attacker can try to exploit this information to recover some information. And the more illustrative case of this kind of leakage is for cache memories, where when we perform an access, the duration of the access can represent an information like the presence or not of the data in the cache. Finally, to tackle this problem, our approach is to modify the instruction set to introduce a new notion of execution context that we call DOM. And the idea is to allow to the software at any moment to give to the hardware some information of its constraints, of its security needs. And finally, it takes the form of new dedicated instruction and register. And during the execution, at any time, instruction and data which are manipulated are associated to a particular DOM, and the hardware has to deal with that to ensure that the isolation is respected. On the hardware side, we have to modify the shared resources to adapt to this new information. It can be reasoned in three design strategies. The log strategies, which allow to allocate exclusively the different resources to different executed security domain. So finally, we don't have more contention possible. We have the split strategy, which allow to partition the different resources between the different DOM currently executed. So here we don't have more exchange between consider isolated execution domain. And finally, we have the flush strategy, when at the end of the execution of a security domain, we remove the different trace to ensure that future execution is not able to recover this trace. And finally, we implemented this different strategy in two different core and one with simultaneous multithreading. And to evaluate this implementation, we also introduced a new security benchmark that we call TimeSec bench. And its goal is to, by different tests, target the different shared resource of the system and try to use them as a covert channel between an attacker and the spy. And finally, if this channel can be mounted, it indicates that we have some leakage. And currently, our implementation are protected against some leakage in these shared resources, but more tests are under development to ensure that it can be applied to other shared resources. So thank you for your attention, and if you have any questions.
Thank you very much for that. Very interesting. I guess I'll ask first, are there questions from the physical venue?
Yes. Currently, there is no one raising a hand, so guess everything is clear on our side.
Okay. So on my side, actually, I wonder if you could comment, and I don't know the answer if this is fully relevant to it, but I know there was, with the RISC-V security working group, there was a microarchitectural new working group, and Rowan at least was involved in that. So will this be something that you think could be pushed into actually being a real, this is more than just a sort of example you have, it looked like there was some work into implementing this, to make it available in real devices. What do you sort of see as the future of that or of this work?
Can you please repeat the question?
Sorry, yeah, I had noticed there was some work on the actual RISC-V, like there was a new microarchitectural side channel group. So will this work be really available in more than, just this form, but actually could be implemented in additional RISC-V cores?
So about work in the RISC-V group, here the difference is, for example, that here we try to in the case of RISC-V group, currently the strategy which is studied is the use of fenced instruction, so the ability to introduce instruction to make some difference between before preceding instruction and next instruction, and to make only finally a temporal barrier between the different execution. And here our approach is more different in the case that we try to consider the whole sharing issue. So particularly it is the case of spatial sharing, which is particularly discussed, because a simple view of this issue can be that we consider that we have different core and we isolate the different execution with this solution by simply put the different execution in different core. And here the difference between this approach is that we try to also consider the case of, for example, of simultaneous multithreading, and to finally have a global strategies for any core, and we have to pick some guidelines to try to respect the isolation. And more globally, if talk about our approach compared to the RISC-V group, we both are not exclusive. So finally, nothing in our implementation is particular to our core, so we can perfectly imagine to export our approach to other core. I don't know if I was precise with we.
No, that's great. No, there's no precise answer to my question. I just kind of I had seen that activity. So of course it's always good to see, this work available and being applied as well. Were there other questions from the physical venue as well?
Not right now, no.
No, okay. Yeah, and I guess the final, I had noticed the what was that, the side channel time, the test bench for the timing side channel. That seemed like a fairly recent project. It still says alpha when I look on the repository. So that seemed quite interesting. I don't know if you had any more comments on that actually as a general test bench. I mean, that seems like quite a valuable contribution as well, being able to generate these timing tests for new cores.
Yes, about this test bench, we currently try to export it to the Raspberry Pi 3, and the first result that we have is for some tests, particularly the case is for instruction cache. We have promising results because we can recover the different results similar to the one for our core. But the complexity is when we have to consider some hardware mechanism that we cannot finally control. So, for example, the different prefetcher in the memory, particularly in data cache, which finally generate noise for our bench, and that we have to try to consider to finally export our benchmark to different implementation or architecture.
Got it. Cool. No, that looks interesting then. Look forward to seeing changes and future work there. I guess a last call physical. There's no physical questions.
No.
Movement, so
No.
I'll assume no. Great. Well, thank you so much, Matthew. Very appreciated that, and hopefully another time in person.
Yes.
The next talk in the series, Phi Attack, rewriting the Java card class hierarchy. Joan Dubrel. Yes. Okay. Perfect.
Yes.
We can hear you great, so I'll leave it to
Okay.
you.
I'm sharing. Yes. Okay. So, hello everyone. My name is Jean Dubreuil, and I'm going to present you a Java card attack named Fee Attack. This work has been performed jointly in the CERMA laboratory and in the ANSI laboratory. So in this short presentation, I will explain in a few words the main principle of our attack, which is detailed in our paper. So let's consider two packages. They both have the same name, which is library. And however, each one has a different AID value, which is deadbeef01 and deadbeef02. In each package, one class is defined with one method called confusion. And in both classes, the method return type is object. But in the first class, the method takes an object as parameter and directly returns it. And in the second class, the method takes a short value and returns the null value. So we now add a third package named proxy. Proxy package imports the first library package, and the Fee proxy class inherits from Fee class. This means that in the cap file of proxy package, the library package is imported using deadbeef01 AID, but in export file of proxy package, the imported package is only referenced by its name, which is in this case library. And finally, a last package is created. This package imports two packages. It imports library, but with deadbeef02 AID, and it imports proxy package. An instance of Fee proxy is created, and thanks to the inheritance mechanism, this instance can be stored in a variable of type Fee. On this instance, the confusion method is called. And if we want to understand what is happening here, we need to analyze 2 points of view, the bytecode verifier point of view and the Java card runtime environment point of view. So let's start with the BCV. When creating a Fee proxy instance, the BCV is able to retrieve the class definition from the proxy package. Then, when this instance is stored in a variable of type Fee, the BCV searches this class from the import table of the cap file of attack package. The class is found in the library package with deadbeef02 AID. From the BCV point of view, everything is fine as Fee proxy class inherits from a class called Fee in a package named library. Therefore, when the confusion method is called, the BCV expects that this method takes a short as parameters and returns a reference. On the other hand, the import table of proxy package references package library with deadbeef01 AID, corresponding to the package containing the mother class Fee. Therefore, when the Fee proxy instance is created, the virtual machine finds the class definition in proxy package, and it finds the superclass definition in library package with deadbeef01 AID. And finally, when the confusion method is called, the virtual machine actually executes the method from the package library with deadbeef01 AID, as the instance actually inherits from the class of this package. Therefore, the method takes the parameter given and returns it as an object type. Therefore, the short value given as parameter is actually returned as an object reference value. Thus, when executing this piece of code, a type confusion is obtained. Also, the BCV stated that the loaded cap files are well formed. To summarize, this attack is not detected as malicious by the bytecode verifier, but this is only because the BCV does not have access to the necessary data in order to perform a full verification between the imported package name and its AID value. And this is only possible when using export file in format version 2.2. However, we only present how to obtain a type confusion. We did not present a full exploitation, as the state-of-the-art of JavaCard attacks is filled with attacks exploiting a type confusion, but these attacks are detected by the BCV. Combined with our attack, all these attacks can be used by a malicious application developer without being detected by the bytecode verifier. And that's it. Thank you for your attention, and feel free to contact us if you have any question.
Thank you very much for that. I guess I'll ask again for in-person questions.
Yeah, no, there are none right now. Sorry.
Okay, so I had a question, just sort of at a high level on this. The disclose you mentioned in the paper that there's a newer version of the verifier, but nobody seems to be using it yet, or you couldn't find it. I guess the current version that you looked at, like how widespread do you think the issue is? It would seem everyone's then using that current version that you looked at that is still vulnerable to this.
Yes, actually, today most of the JavaCard products are implementing the JavaCard specification 3.0.5, and Oracle specified the newer version, which is 3.1. And actually, in this specification, a new file format of export file is defined, and in this new format, we can find both the AID value and the package name, and this allows the bytecode verifier to perform this verification. And when we use this version of the bytecode verifier, our attack is indeed detected. But nowadays, most of the JavaCard are no JavaCard products implement this version of the specification.
Interesting. Okay, got it. So I missed, yeah, it was the specification, not the version of the program. So how old is the newer specification version, out of interest? Like,
but actually you can run the bytecode verifier 3.1 for older version of JavaCard specification. So products that are on the field today can be secured by using bytecode verifier 3.1. Yes.
okay. I'll switch back. Any questions from the venue on?
Not right now, no.
Not right now. Okay. Okay, with that, I think we'll thank you for your talk. We heard the end of applause there. It sounds like maybe. So thank you very much. Very interesting work.
Thank you.
And we'll move on to the final talk of the session, enhanced encodings for white box designs. And Thomas, I believe you're there. Yes.
Yes, can you hear me? And do you see the slides?
We hear you, see the slide, see you. So perfect.
Okay, thank you. So hello everyone, welcome to the presentation on how to enhance encodings for white box designs. So the context is white box cryptography, where the execution environment can be totally controlled by an attacker. And by extension, it is an implementation designed to resist in such an environment. And so the goal of the designer is to realize an implementation resilient to key extraction. In 2002, Shaw, Johnson, and Van Oorschot introduced a new way to implement cryptographic algorithms. And for that, they provided an initial solution to the problem of obfuscated program, and they used tables to perform computations. And so they introduced the key concept of encodings, which hide the sensitive content of the tables. From them, numerous propositions of white box designs have been submitted in this literature. And we can note that all of these propositions are theoretically broken. So our proposal comes from the simple observation that any Boolean function can be expressed as a logical circuit only composed of XOR and NOT gates. And so our idea is to consider cryptographic algorithm as a logical circuit and to use a semi-homomorphic encryption scheme based on the addition property to perform computation in the cipher domain and so securely. Why the addition property? Because with that, we can have all of these three gates. By adding a bit X with Y, the result is the concatenation of the end of these 2 bits followed by the XOR of these 2 bits. And when we add X with 1, the result is this bit followed by the inverse of this bit. So we need a semi-homomorphic encryption scheme, and which shows the binary crypto system. But we had to modify it in order to fit it in the whitebox context. And so this is the modified binary crypto system, where the public key is a prime number P, a quantity R, and 2 random numbers T and Y for the private key. To encrypt this message M, we just compute T times Y to M modulo P. For the decryption, we remove the quantity T and only keep the exponent of Y thanks to the logarithm. And we can see that we keep the addition property, the semi-homomorphic addition property, by when we encrypt M0 times the encryption of M1, the result is the encryption of M0 plus M1. So now we will use this modified crypto system in order to create an encoding. To encode the bit A, we just encrypt 2S plus A, with S a random number. For decoding function, we decode the encoding of A. The result is the exponent of Y, and we just compute modulo 2 in order to just have A and the least significant bit of the exponent of Y. So the strategy is simple. We will encode each bit of the message, and as you know, we consider cryptographic algorithm as a logical circuit, which gates are modified binary encoding, and we can evaluate each gate, XOR and NOT, under this modified encoding. And now we'll see how to evaluate these gates. For the XOR implementation, it's quite simple. We just have to multiply 2 encoded bits. Indeed, thanks to the addition property that we have seen sooner with A plus B, the least significant bit of the exponent of Y is A XOR B. And we can evaluate an arbitrary number of XOR gates just by multiplying each encoding between them. We can add that for the NOT implementation, it is sufficient to multiply an encoding, the encoding of A, by an encoding of 1. For the AND implementation, we need tables with P entries. And these tables will perform a right shift. We right shift the encoding of A, of B, and the encoding of A times the encoding of B. And then, by multiplying all these 3 encodings, we'll have the encoding of A and B. Indeed, with the addition property, we have the XOR of these quantities. And so, here are the results. And we can remark that for the NOT implementation, we just have to remember that we wanted to perform a NOT, and to the next table, to the first table method, we can integrate it in these tables. To summarize this presentation, we suggested a new encoding scheme based on the binary crypto system. We keep the semi-homomorphic property of the original scheme, which allow to drop tables of the XOR operations. And now we can compute any cryptographic algorithm designed as a logical circuit. And so in the paper, we provide an example with the AS128. We provide the security analysis, and we can remark that this security can be adaptable by choosing, for example, an IRP, and our design can be easily adapted to a masked implementation. Thank you.
Thank you very much again. Very interesting. So with that, we'll do a call to the physical venue for questions.
Yes, we actually have one. Give us a second to
Great.
bring a microphone.
So we had to get the virtual physical interaction at least once.
Hi, thanks for the presentation. So my question is, since you mentioned that all white box schemes have been practically broken, basically, yeah, for how long do you expect your encoding scheme to be considered secure? Because it's not a criticism, right? It's just a realistic question of thinking.
I know.
Everybody makes big efforts, but it's hard, huh?
And so I don't think that our proposal is more secure than the others. And with the security analysis, we quantify that how much an attacker can break our system, and we can, with the AS128, we chose a 6-bit prime number P, which was 553, and with 53 we had the same level of security than the others.
Yep, thanks. That answered the question.
Are there other physical questions, or is that?
No, not right now.
Okay. I wonder if you could comment. So looking in the paper just at the example implementations, for the AES implementation, did you end up actually implementing it on the device, or because I saw there were some sort of estimated times for various configurations and memory allocations?
Do you ask for? We implemented it, but not in a device, just in computer. And with our proposal, we can say that we show that the speed is always the same. Only the memory consumption, whatever the speed is always the same, whatever the size of P. Only the memory consumption can be in function of P.
So I guess you can tune that a bit for devices as well as security requirements.
Excuse me, can you repeat, please?
Oh, sorry. No, just a comment. I get it. So you can tune that a bit, I guess, is the one other advantage for devices that have smaller or larger memory sizes available. In addition to security requirements you need.
Yes, sure. For example, we implement two versions. One version without countermeasure and a maxed version, and we see that the memory consumption is not very, very higher than the first one.
Great. Were there other in-person physical questions?
Unfortunately, no.
I don't see any on Mattermost, so I'll first say thank you again very much for this great presentation. We're actually a little bit ahead of time in this session, so I don't know if all the other paper presenters are still available, but I was going to say if there were questions people thought of for any of the talks, we may be able to ask them.
That doesn't seem to be the case locally here in Lübeck.
Right. I guess for me this is early, so I'm ready to go, but I guess for you, what is this? Is this just before lunch? I'm holding up your lunch.
Yes, yeah, we will go for lunch as soon as this session is over. So I think we can give the authors a round of applause. I hope you could hear it this time. Yesterday, WebEx just canceled it out because it thought it's just background noise.
No, we did for sure.
Perfect. Yeah, then thanks again and see you later, I guess.
Yeah, thanks very much and enjoy the rest of the event.
Yeah, thanks, Colin, also for hosting the session and getting up early, right? So I think you're already done. Yes, so we'll have our lunch now in the lunchroom. So that's around the corner, walking down the hallway, and we'll continue at 1:30 with the keynote. Yeah, also in the stream. So see you soon. Thanks, and enjoy the lunch if you're here on site.
So, okay, so now it's a pleasure to introduce our next keynote speaker, Axel Poschmann. He will talk about lessons learned from securing the supply chain of a high security smartphone. Axel is currently working at Zenith Labs, one of the leading security evaluation and validation laboratories in the Gulf region. And before that, he was working on security at NXP Semiconductors, and he was also assistant professor at NTU. And yeah, Axel, the stage is yours.
Thank you, Thomas. It's a big pleasure to be here. When the other Thomas asked me to give a keynote here, I was really, really excited. Some of you may know I used to be part of this amazing community. And between 2006 and 2014, I was actively contributing as a researcher and publishing at CHES, CARDIS, and so on. And then 2014, I made a transition from academia to industry, and that changed my perspective because I was working more and more on more and more applied problems or more and more applied aspects of the same problem rather than looking at the technical solutions. So that's also the first thing I want to put up here, the change of perspective. And I think my change of perspective on side channels is a good example. So this is a paper from 2007 that I co-authored. I think it was published at Samos or so. And what I wanted to do here is to set up a design flow so that cryptographic functions can be automatically placed and routed with a dual rate technology called MCML. And then we try to evaluate the side channel resistance and the gains of it. So that's a very specific approach and, optimizing a technical problem. That was my view on side channels 14 years ago. And that changed a bit. And it changed in particular since I have kids. Kids are great side channels, as you all know, right? You tell them a secret and everybody knows it. The kindergarten teachers, the parents, everybody knows it. So every morning when I drop my son at the kindergarten, I actively exploit a hardware vulnerability through a side channel. And that sounds scary, but if you look at it, it's as simple as this, right? So this is actually the pin pad to enter the compound of the kindergarten. And you can clearly see what's the pin code, all right? And it is a side channel, and you don't even have to check all the 24 different possibilities here. It's 2580 every morning. I don't have to remember, oh yeah, side channel analysis, and you're going. So why do I bring this up? This is a non-technical problem, but it's exploited every day, right? So, and the solution to this problem is definitely not technical. It is more quality, processes, maybe you should use better paint or a different approach for the keypads altogether. So it's a very applied solution that would make a big impact here. And I put this up to manage you guys' expectations on this talk because I haven't done research since 2014. I haven't published anything since 2014, but obviously I use my researcher's mindset to tackle problems. And one of the biggest challenges I had in the last couple of years was the supply chain security. And that's what this talk is about, on the technical, economical, practical aspects of supply chain security. So first I'd like to quickly introduce Zenith Labs, where I work. Then I'd like to introduce a high security smartphone that we are looking at. And then we look at the supply chain security model. And then we zoom into three different aspects: the factory, where it's manufactured, the logistics aspects, and then the testing scope. And then finally I wrap up with some lessons learned and some open challenges. So Zenith Labs is 5 years old, and I think many of you based in Europe, all these labs in Europe have a high quality, but there's none like this in the UAE or the GCC region other than Zenith Labs. So I would say we are on the same level as a typical European test and validation lab, and that makes us stand out in that region because we use also cutting edge research to enhance the testing validation activities that we conduct through the entire attack surface, hardware, software, crypto signals, and also the entire life cycle of products. And as usual, this only works with high quality people, cutting edge equipment, and processes. So this is the 4 labs that we have, and you can see we do everything from software security, then device security, embedded security, chip security, X-ray analysis, fingerprint, supply chain security, And then for signals, it's everything like radio signals, RFID, NFC, Bluetooth, and also we have a crypto lab. And yeah, we have riskier equipment, right? So like everybody else, but this is a highlight. So I skipped that a bit. We also have a wet bench, so we can do chemical encapsulations and stuff. We have a precision microscope, probing station, and so on. I'd like to focus a bit more on this slide. So the guys in the lab have a lot of certificates. That's particularly important for software security, always the latest certifications. We've done more than 100 assessments of products. So we actually work on exciting projects. And mostly the software guys, but also hardware, signal, and cryptos, they've published together in the last 4 years more than 33 zero days through a responsible disclosure process. So we have 33 CVEs assigned to Zenith Labs. And there's a new one coming that should be interesting for some of you in the audience because it concerns manufacturer of a high security smart card, so a high security semiconductor company from Europe. And this disclosure process took a bit longer. It wasn't the usual 90 days, but it was 1.5 years. There's a hardware vulnerability, so it takes longer to fix it and mitigate it. And that CVE will be officially published in 2 weeks from now, today, at the Hack in the Box conference in Abu Dhabi. And it's also everything aligned with the manufacturer. So stay tuned, that's pretty exciting stuff. We're 20 people in the lab, so rather small, but we come from 10 different nationalities. So that brings a lot of different diversity and perspective. Okay, let's have a look at the smartphone. So I brought one of these. So this is the Kadim phone, the first one. And when I started in 2017 in Abu Dhabi, they dropped me a phone on the next day and say, look, now make a hardware security plan. I said, okay, let's do it. So then 3-4 days later, I was done. And yeah, anyway, there's a successor from this phone as well. 2 years later, the Kadim R1 came out. It's like an ultra rugged version, but inside it's a lot of new things have been improved. And this is meant also for first responders. So you can use it on oil rig or in a firefighter department. So it's very tough. You can drop it from 2 meters. Let's have a look on the security of this phone. So it's rooted in tamper-resistant hardware. So even though it looks like a normal phone, there's a lot of tamper detection and prevention countermeasures built in. And obviously we tested all of them and assigned some ratings to them. Then a hardened bootloader is executed to facilitate a secure boot. On top of that is a customized Android hardened operating system. And then only a subset of apps can run on this phone. These are all hardened, custom made. You can't run Facebook on this phone, but it's just hardened apps that go through a customized app store. So a curated set of apps that are all tightly controlled. And obviously there's frequent security patches to make sure they're secure. And all of this is embedded in a customized mobile device management solution. So you can have like fleet management, you can use metadata to make sure the phone hasn't been compromised. This is all from the website. I won't go through it, but you know, there's the secure element to store the secure keys, multi-level hardware tamper protection, secure boot, runtime integrity protection, application installation, frequent software update, MDM, and secure app store. So let's assume this phone is secure. And again, I made this test plan. And after a couple of days, I was like, here's the test plan, and you know, now we can execute. Now we can go and buy the equipment and hire the people to execute it. But the results should come in within a few months, so that was also a challenge. That's not the focus of this talk, because then at some point they said, look, what about supply chain security? I said, yeah, what about it? It's exciting. And they said, yeah, what's your plan? And I said, okay, what do you got? What is the current state of the supply chain security? And then my colleague made a drawing at the whiteboard, and she drew this. That's our supply chain security process. So you manufacture a phone, then we bring it to Zenith Labs, you do your thing, and out comes a secure phone. So that was the supply chain security state when we started. And I said, okay, this sounds a bit like Harry Potter. I don't know if we can make that work, but let's see how we can build on this. So if you think about it, it's always good to have a greenfield approach. So we could really start from fresh. And yeah, time was ticking. So what can you do? Yeah, so then we build a model. So a very simple model. You have the suppliers of chips, of components, the printed circuit board, a battery, the housing, and all of that goes together in the factory of the manufacturer, the ODM. And then the phone is shipped to the UAE, and the final steps of the assembly happens in our premises, the provisioning and all these things. So the vendor in this case is our mother company, Digital 14, and we are in between, and obviously along the line to make it secure. And then finally it's shipped to the customers. And yeah, so here we have good visibility. Digital 14, it's my colleagues, we can work together, we can have a look, we can improve things, we can change things. But here, manufacturer and suppliers, not so much. It's more of a challenge. So in particular, you don't have any control over the suppliers, because if you say, I want some changes, they say, yeah, how many million or billion devices you want to buy? A few thousands maybe? Okay, so no chance. You don't have any control over the factory, not a lot, but we'll see how to change that. And the logistic is also a challenge because somebody has to ship it from the country of manufacturing to the UAE. So that means when you get the phone in our lab, what can you do to improve the assurance? You have to take it apart to see if that's what's inside matches what was it supposed to be. We have all the design files. That's exciting because the vendor is us pretty much. So I can see all the printed circuit board designs and layouts and components, bill of material, and we can check if that's exactly as we wanted it to be, right? So, but that requires destructive testing. It's a lot of effort and it's definitely not scalable. So, and overall it leads to low assurance. So what we did then is to improve on that. And the goal is pretty much simple. You want to move the assessments as much to the left as possible, as much over here towards the supplier as possible to have checks, and then you take control and see how you can manage that. So you still have no control over suppliers, for sure. You have better control over factory, and we zoom in a few slides to see what you can do. And you have better control over logistics. And again, we also zoom in here what to do. Then there's non-invasive testing. That's the goal, obviously. You want to not destroy the phones, but you want to make everything checked. So every phone is checked, which is less effort and definitely scalable. And all that together should lead to higher assurance. So let's zoom in on the factory. So as I said, I used to be part of this community. What do you do when you have a factory and you want to make it secure? You turn to GIL and you take the minimum site security requirements, right? To see what happens. So now imagine you have a factory that is specialized in electronics, and you take this absurdly tight yardstick of a minimum site security requirement and apply it to the factory. So what comes out, right? Yeah, so we hired a company from Europe that is accredited to do these MSSR audits, and we did an audit of our factory. And what came out? A lot of surprises. So, and obviously the biggest surprise for me was that we had so many passes and so many passes with issues. I would have assumed it's much more red and much more, failures along the lines. So when I saw it, I was like really surprised positively and thought, okay, what can we do? So the first learning is then when we flew to the factory and did this audit and so on, is that factories have actually really good operational security procedures. So it's really difficult to do something in the factory that the factory doesn't want you to do. The problem is the threat model is not the right one, right? Their threat model is theft. They want to prevent their workers from stealing things and selling it on the black market. Because if there are some chips running around, they cost maybe $100. That's already a lot of money. So all of that is optimized against theft. And there's no focus on supply chain attacks. And that makes sense. From a factory owner, it makes sense. Theft is measurable, it's money. You can see that, loss. But supply chain attack is some obscure advanced persistent threat, nation state, who cares, right? So how can I measure that? So turns out it's very hard to smuggle something out of the factory because that would be theft. But as an employee, it's kind of possible to smuggle small things in and exchange things here and there or something like that. That was something we had in mind. So in a nutshell, the operational security procedures are really, really good, but they need to be tweaked a bit here and there. So how can we do that? So we sat with the management and asked what we can do, and they're very happy to provide additional security features for a fee. It's all about the money. And then you get your separate parts storage areas, you get your separate assembly line with extra access control and 24/7 CCTV footage that is stored. You get secure storage in there so that critical components can be stored away. And you have a separate packaging and outgoing shipping area. So that's pretty much the things go in, they're stored separately, they are controlled, it could go on your assembly line, and then they go for shipping and go out. So that looks like everything is under control. However, there are a few parts that are not separate and they cannot be made separate, and that's the SMTA, so that's a PCB SMD component assembly device and testers and these things. And the reason is they're highly utilized across all projects. This is where the company makes money. They have 20, 30, 50 different customers and they all use this machine. So when we said, look, we want to make some changes here and there, they said no. I said, okay, how much do you need? How much will it be? Tell me. We are happy to pay for it. And they said, no, we don't do it because it would risk not only your project, but also other projects. And so we don't change anything here. And that's, unless you have a big million pieces, 10 million pieces contract, you probably are able to change it, which we didn't. So it wasn't possible to change that. So what we did then is went back with these constraints and had a look at what we can influence and what we can't, and how can we change the assembly manufacturing process in order to increase the testability, visibility for supply chain security. So we added additional steps in the assembly line where we can do what we want, and in the outgoing packaging and outgoing shipping area. So now we are from the factory, and now the devices are supposed to be shipped to the UAE so they can be finalized in the UAE. What could happen on the way? Anybody has a clue? What could happen? Nobody read the Snowden papers? Interdiction, yeah, exactly. So this is a photo of NSA operatives. They just caught a Cisco router and they're just flashing new firmware on to make a supply chain attack, pretty much. And this is known since 2013, since Snowden. So you want to control your shipping from the factory to your home. And we were looking around, and I was sure there should be some solution, and this looked very promising. This is a small device here that records the exact location, so you can see shipment is diverted or not. It records the temperature and light, so if the package is open or not, the humidity, then the pressure, so you can see if it's in the air or not, and shock. So then you just put it in a box in the beginning in the factory, and then throughout the journey, at the end, you just take it out. In between, the device is continuously sending the data to a web interface, so to the cloud, so you have data in real time, which I found pretty appealing and pretty cool. So we met with these guys and thought, okay, what can you do? And then things became clear that this is not suitable, because first, in the country of manufacturing, GPS is controlled by military, so it's not available. That means from the factory to the airport, there's no GPS recording. Okay, okay, fair enough. Maybe we can get away with light sensors and the other stuff so we can see things. Then the next thing is also it's a feature that during flight, there's no data transmission. And that's a feature because it's regulatory requirement from the, I think, IATA, that battery-operated devices are not allowed to send stuff during flight. So that is another feature that it automatically detects that it's during flight. So that means you get real-time data here, but not location, and you don't get any data here. Only when it lands in the UAE, you get your data as a batch uploaded to the cloud. We thought maybe that works, but then it turns out this device is not tamper-proof. So, and there's test interfaces, debug interfaces. So, yeah, I mean, clearly somebody could go here, do some stuff, or even during the flight, and then just load a bunch of fake data on it and nobody would notice. So that didn't cut it for us. So, and it's pretty expensive though as well. So then that wasn't worth it. So then we came up with our own solution. So, and we call it Track Attack because it's a tag that tracks stuff. And it's also not tamper-proof, but there's some nice tricks how to correlate the data and so on. And this device is super cheap, and you would put it in every device of the phone. And then when the phone arrives in the UAE at the provisioning stage, it will be taken out of the box anyways, and then you take the beacon out and you analyze the data. So it's not live, but it's very hard also to manipulate. Yeah, all right. Now let's have a look at the testing scope. We use the hardware lab, the signals lab, and the software lab for this. So the hardware lab obviously looks at the hardware, the components, the markings, the laser marking, X-raying, solvent tests. You check if it's counterfeit or not. There's lots of literature out there to do these things. We dump the firmware, and then the software lab analyzes firmware images, compares if they are the right one or not. And the signals lab would take some of the devices and check for covert channels and tampers. But again, for hardware trojans, it's very hard. Is it triggered or not? So it's a very tedious process. And we call this high assurance supply chain security because it's destructive. The hardware lab would destroy these devices, and they're not cheap. So the company would always say, how many do you need? You really need so many? And yeah, we need so many to make it, to get the data we need. It's very slow. It requires a lot of effort. It requires a big lab. And then you do some kind of chemical test and stuff. And a lot of reverse engineering, which is also not the most efficient thing to do if it's not automatic. And because you destroy the device, you can never do it on all the devices. So it's probabilistic. So you have to sample, and then you have to extrapolate your assurance out of it, which is maybe not that good. It does a trick, but it would be better to scan and verify each and every device, right? So let's have a look at a hypothetical example. So these numbers are all made up, right? So let's assume you want to manufacture 7,000 phones. They will be produced over several weeks and will be shipped in 11 batches. The batch sizes are here. You can see in the beginning there's a problem with the production, and then they increase the capacity until they reach final capacity. And it takes a couple of weeks and 11 shipments before all the 7,000 phones arrive or will be ready for shipping in these batch sizes. Now the question is, how many phones should you sample, and which ones? So that was a big question. What do you do if you have statistical questions? You go to a cryptographer. Right? So I went to my crypto team and said, look, I have this problem. And they give me a few days, and then 3 days later, here's the model. No, it doesn't work. Another 3 days. It took them 2 weeks to come up with the right model, which is the hypergeometric distribution. So here you can model per batch. You can model different batch sizes of n. You can model the number of samples that you draw from that batch. And then you can determine the probability that 0, 1, 2, 3, 4, whatever devices are malicious when you do this sampling. The only problem is now, how do you model the number of malicious devices? We don't know that. So how do you do that? Oh, by the way, this is a small side note. Turns out this scenario, which took my crypto colleagues and me like 2 weeks to identify the right formula, is exactly what MBA students learn in their statistics class, in the first statistics class. So there is value in doing an MBA, I would say, because this is exactly the thing MBA guys learn. Because if you have a bunch of light bulbs, you want to figure out how many are meeting the quality requirement. This is exactly the formula you use. Anyway. Yeah, so in order to get the adversary model, we defined several adversary scenarios. So let's assume a very powerful adversary that knows exactly which phone goes to which person, and then he just maybe wants to target that single person. then the adversary only needs to modify a single phone. Why wouldn't he do all of them? Because in our model, we assume once we test, we would for sure identify a malicious phone. So if it's 100%, there would be 0 chance of success for the attacker. Another model would be 1 phone per shipment. So we didn't know which one, but if one of the phones in one of the shipment, sorry, if in every shipment there's 1 single malicious device, and then we modeled different uniformly distributed amounts of devices, 1%, 5, 10, up to 90% of all manufacturers' phones are malicious, and they would be uniformly distributed among all the batches. And the reason is that you want to reduce your detection probability. So this would be for an attacker's gain. The more he has, the better. But obviously, the detection probability is worst here and best here. So he would strive somewhere for in the middle. And now we need to answer management how many phones we want to destroy, how many we want to draw, and what is a good cutoff and trade-off. So let's have a look at what we proposed in this hypothetical example. So again, we have our shipment schedule, and in this example, we assume we sample 1% in every batch. So there would be 1 here, and then if it's 350, we're on the safe side and take 4 and 5, and so on. So in total, you would draw 72 phones out of 7,000. Not too bad, but it's also pretty pricey, so they're not happy with it, and will always pressure you to do less. So in this example that I just described, then this would be the success probability of detection of at least 1 phone throughout the whole process. And if you look here, then this means pretty much if 5% of all manufacturers' phones were malicious, then this sampling strategy would detect at least 1 of them with a probability of 97.61%. Now the question is it good enough? I don't know. We provided this data for this real data, obviously, and said, look, management, now you have to decide. Because I don't know where to take the cutoff or not, but this is how you can model it. And obviously, it would be better to have absolute certainty, and that's why we need scalable supply chain security that's non-invasive, fast, efficient, deterministic, so you have 100% coverage, should be integrated into the manufacturing process so that you can generate data before it's packaged up and so on. For example, automatic optical inspection, I think, is a pretty cool tool. And then 3D X-rays, all these kind of things. And yeah, we got in 3D X-ray, and we also do some X-ray scanning on the phones, and now we scan each and every phone that comes in. Will be at least X-ray scanned. You cannot detect everything, but you can detect a lot of things. So that's already a significant step up. All right, I'm a bit ahead of time, but I'm still wrapping up. I think everybody appreciates a longer coffee break. So what are the lessons learned? Factories have very good operational security. That was for me the biggest takeaway when we were there. But they use an unsuitable threat model. And then you have a lot of practical reasons, and on top of economics, then introduce additional constraints, so you cannot just come up with an efficient solution. For example, don't change the running system. That's something we never assumed, and that was a big takeaway. I think close collaboration with manufacturers or ODMs is required. You need a good relationship to go in and change things and see what's possible, what not. There's no satisfactory logistics tracking solution available. That's something that is unsolved. And for me, a personal takeaway is if you have a simple question for simple statistics, don't ask cryptographers. You know? Just go to the business guy, because they will have the answer straight away. Right? It's not that complicated in that case. All right. Open challenges. I think there's a lot of room for research, very applied research, I give you that, but that would have an impact. For example, the offline tracking solutions that are, suitable for in-aircraft tracking. Then design for verification. I think there needs to be a very close collaboration between designers and manufacturers of products that you design for testability or design for verification, so that you are able to generate the data that is really important efficiently, and then are able also to efficiently reproduce it at the end again. And then the question is, which of these data are actually relevant and can we produce and validate efficiently? Is it weighing? Does it make sense to weigh this thing with a microscale, or 3D electromagnetic, or what other non-invasive measurement technologies are there to generate the data that you need to get assurance? That's it. I'm already done. Thank you for your time, and I'm open for questions.
Any questions from the audience? Ah, yeah, over there.
Thanks for the talk. So you described very nicely, interestingly, the process that you set up. How do you test your process? Do you sometimes like introduce modified phones and then check if your process actually catches those, or you just say, you know, I made it, it must be great? Or?
Yeah, I mean, how do you want to test that? I mean, you want to produce a malicious phone in China and then see if it pops up?
Well, you can do the kind of interdiction thing, right? That just before it arrives to your company, you actually have an interdiction team.
We haven't tested that. But what's interesting, we found a lot of quality issues. So to answer your question, so we don't do these decoy thingies, but what we've done with the data, we found some misalignment between the design and the product, and then raised an alarm, and it turns out it was just optimizations. There was a functional reason for it, and we ruled out that it was malicious. It was just, I don't know, the antenna was then better or something. So you can find a lot of small things, which then mean you need to have better control over other things in the supply chain earlier to make sure you see these things.
Yeah, but so how do you establish trust into your process? That you say, I believe by doing these measures and following these steps, we would have a very high probability of catching malicious modifications.
Well, it's a good point. I mean, I establish trust exactly the way I did here. This is the math behind it. This is the model. There's always, you know, we might have overlooked something. The model might not be perfect. But again, I mean, how would you model this? I don't know. Who would, maybe, yeah, maybe.
No, I don't know. That's why I'm asking.
Maybe you need some kind of a capture the flag competition. How you would, you know, subvert a supply chain and these kind of thing. But I read all the literature from, in Florida. There's this institute. They have a lot of cool stuff exactly on this topic. So you know, that all went in, but yeah.
Yeah, but maybe a competition would be a cool idea, right? That you say.
Yeah, for sure.
Here are phones, modify them, try to get them through our thing without being detected. You get some money for it, right? And you get lots of creativity.
Yeah.
Thanks.
I think you underestimate how much effort it is for each and every phone. It's not like it's cheap or, you know, or people have nothing to do. You know, it's a great thing to do. I agree, but it's a hell of a lot of that effort, right? So if we have something really efficient and scalable, yeah, I'm all yours. But until then, there was another question.
Hey, thanks. So I was wondering, when you were evaluating the factories, what was the threat model you were considering? Because it seems like you were trying to defend against malicious employees. I got that, but what about, say, a malicious supplier? Or
these are exactly two of the aspects we considered. It's like, how can we make sure that all the items that go in the factory are trustworthy? And there is already a sampling procedure in place, so that's also one of the reasons why they are pretty high in MSSR, for quality reasons, because it might be that they're counterfeit products or lesser quality, or I don't know. There's an elaborate framework for quality and economic reasons set up in every factory to check the incoming goods. And we just piggybacked on that and put a few things for security on there. I don't know, you check also the solvent tests with packaging, is it the same across the batch? I don't know, these kind of things that you could do. So that's for the suppliers. But then again, everything, we try to go down for some key suppliers a bit further. Everything there gets really, really difficult because they produce billions of devices, billions of chips, and they wouldn't do anything for a few thousand or 100,000 things. So then at some point, if you say, okay, we have to live with a certain probability that it's malicious, and then focus on how you detect that, right? And that is why we have this testing and so on and so forth. But to your second point with the employees, exactly, that was the second one. Threat model would be one of the employees got paid by whoever to, let's say, exchange a few of the components with a different firmware on it, or these kind of things. And then we looked at it. I mean, at the SMTA, you have these reads where this things goes in. So we looked at how does it come from the secure storage, when is it here, who has access. So it's mostly operational security procedures. And they are actually already very tight because they don't want people to steal things. I mean, a chip from Qualcomm is a lot of money, right? And if you just take 10, you already have a lot of money. So this is already closely monitored. Then the question is how we can prevent swapping and how you can things out. And so this is what we focus on. It was mostly malicious insider employees, maybe management, this kind of things.
All right, thanks. And then the second question I would have is, given that there was also supply chain attacks when it comes to software, right?
Yes.
How would you maybe say transfer now the learnings that you have to the software world? And could you give your take on that?
So in software, it's actually much easier, right? Because you always get the binary, right? But you can also ask for source code, and then you have to go through it, and you have to check it. And that's what we do. For everything that we can do, we go through each and every line of code. For the apps that we produce ourselves, we do that. And for others, at some point, you have to rely on open source. Right? I mean, Android has, what, 12 million lines of code? So yeah, you could go through it. But there is some levels where you need to rely on community efforts. But in general, for software, whatever comes in as a firmware or as a building block, wherever we get the source code, we will check that for sure.
All right, thanks.
I have a question about the logistics.
Yeah.
You said that well, you cannot guarantee that the device is tamper-proof or anything.
Yeah.
But during transport, the only thing you really need is a tamper-evident packaging, right? To avoid an invasive attack, at least.
Sure. Yeah.
And that should not be hard to fix. So, I mean, you wouldn't need all this monitoring if you had a tamper-evident packaging.
Yeah, but you can fake the tamper-evident packaging. It's a sticker, right?
Well, there are ways to make tamper-evident packaging other than stickers.
Agreed. We also look at that, to use some low-cost packaging to do that. We haven't done that yet, but yeah, it's another very interesting area. I don't know, where you can use a paper as a puff or something, right?
Yes, you could use crackling paint or glitter,
Exactly.
glitter or stuff.
Like the glitter spray.
Yes, they use it for nuclear weapons back in the days, for example. It is not very hard.
Yeah, I agree, but in the end, when you have these phone covers, they go to a customer. They want glitter spray on it, right? They want it needs to be shiny, and So there are some constraints on it, but I agree. There's a lot of things that can be done as well. That's good.
Any further questions? Oh,
yeah, two.
Another one.
Hi, thanks for the talk. I was wondering, you were talking about like securing the logistics. How do you secure the logistics side of going from your labs to the customer? Like, because you showed it's secure, like, do you give it to them personally, or like, what's the process there?
Yeah, so that's a good point. So all the customers at the moment are in the UAE, so we can hand deliver them, 100%. And again, the phones, once they are finally provisioned and set up, they are part of a mobile device management system. So you can monitor the devices if you want that, or if the customer wants that. They can gather a lot of metadata, like location and all these things, if they want that, to correlate that with, is the guy really in the office, or is he traveling? Why is the phone using this? Behavioral security kind of things. And this is for the life cycle, and for the delivery, yeah, we just hand deliver it to the client.
Thanks.
Maybe I should add, these phones are not available on Amazon. It's for large companies that takes at least a few hundred or 1,000 phones because you need all the server backend infrastructure, the PKI must be set up properly, and all this stuff. This is very expensive, and also the maintenance of this is also, I wouldn't say it's not worth for a private person to go through this probably.
Thanks for the talk. I was wondering, so I guess that for the phone you have to outsource some parts of the components. How do you select companies that you ask to design some part of the phone? And how do you ensure that they are trustworthy?
That's a good point. So there is, most of the components are standardized, right? You cannot design your own Qualcomm chip or MediaTek chip. That's simply not possible. Right? Apple can do that, yes, but we cannot. So you have to buy certain components that are off the shelf, and sometimes that requires more other components. And then some aspects, like the temper mechanisms, we fully do ourselves. So everything for the temper, the design, that's very closely guarded. Nobody sees that, and this is designed by our own team, not Zenith Labs, but Digital 14, and then it's just manufactured by the manufacturer, and that uses then again standard components. And here it's the same as what I said previously to the other question. At some point you need to trust these guys and hope that by sampling and cross-correlating you would identify a counterfeit or malicious device. There's no real good answer to it, unless you do everything yourself, which is not possible.
Okay, thanks.
Yeah, one more question. I guess it's actually also in the same direction again. So there's a lot of literature on hardware Trojans, right? Is that something you can actually test for? I guess Qualcomm is not going to give you the blueprint of the chip either, right? So.
Agreed. So there is some challenges. We have done everything we can. So there are some areas which are very hard, and honestly, there's a whole lot of literature on hardware Trojans, and I was contributing to that 8 years ago and 9 years ago, right? Which is, I would say, sometimes a bit hypothetical, because before you change the netlist to do something, you will probably find other means to break the whole system. Because maybe you don't need to break the chip, but maybe you just need to break somewhere else in the system. The bus is not encrypted, or I don't know. So there's easier, what is it, Mackenzie's razor? Or there's this rule, if there's an easier way to do it, it will be done this way. And this is why I think, like, in-chip hardware Trojans that are maliciously done in a factory is probably can be addressed later. Let's put it this way.
Thanks. Maybe one short follow-up, but I think you also answered that more or less already. So did you ever find malicious things in the phones? Or
We found suspicious things, and we were really like alerted and excited. It works, our process works, right? So we found something, and then it turns out it was a revisioning problem. So we didn't have the latest design files. But this is good because it highlighted that we need more control over that and need to be better in there. It was just somebody changed the PCB line somewhere, and whenever it comes to PCB lines, it could be immediately an antenna, right? There's also in the Snowden leaks, there's a lot of literature where they just add a small transistor here or there, or add a few things, and it immediately becomes a transmitting device. So we were really scared, but it turns out it was just a quality improvement, and we verified that 10 times over. So yeah, we found these kind of things.
Just wanted to say, so Eve convinced you successfully that it was just a revision, right?
Yeah. The malicious insider paid by somebody, yeah, they convinced me. No, we had different people cross-check that. They would have been all been paid for, right? So.
So I would also like to ask a question in this direction, because you said you're a side channel guy, and there's also some work on Trojan detection or detection of malicious components using side channels. Have you looked into that and thought about applying it?
No, but yeah, I used to work on this, yeah, but I'm not a side channel guy. Thomas would say I'm not a side channel guy, and Benedict as well. So no, we have not used that, but what we find side channels. So when we do the Tempest setup, where we look at electromagnetic emanations and so on, we look to try to uncover covert channels, which are side channels in a way. but we don't use side channels to find them. We just use normal means to uncover side channels or covert channels if something is transmitted. Yeah.
Thank you. So are there further questions in the room? Yeah.
My question is, how do you think academic cryptographer can help on these problems? I mean,
academic crypto work?
Crypto, I mean, CARDIS community. How can
blockchain.
we help?
No, I'm just kidding. IoT and blockchain, no.
You definitely turned out into industry.
No, but I mean, in that area, like attestation and, how can you use certain features of the hardware to build a root of trust across the system and across the logistic chain? I don't know. I mean, I don't have the answers, but that could be something. Maybe you can compute, multi-party computation, that certain things need to come together so that it's validated. I don't know. Yeah, there's a lot of actually very simple things that need to be solved, and I guess maybe a proper crypto protocol could solve that. So when Thomas asked me about side channel to use, that's already very, very sophisticated. I think there's much easier low-hanging fruits that can solve problems. Yeah.
Okay, thanks.
The side channel guy.
Almost. So, because you mentioned that you do now this 3D X-ray stuff.
Yeah.
Yeah. And so, is there any physical modification that you cannot detect with the 3D X-ray? Because I mean,
Probably.
so the software, you dump the software, you can compare the software and so on. So that's done. Checkbox. What remains is physical modification.
Yeah.
And with an X-ray, are there things you cannot see?
Yeah, I mean, the X-ray has a pretty high resolution. I think it's 20 microns. So if you modify something below 20 microns, that's it. But I think 20 microns is pretty good as a first shot. But I think there's also opportunity for people to do that even smaller and more, I don't know how to say, more sneaky. So that's why we don't trust 3D X-ray completely, right? There's always more on follow, but it's a first shot and it's good, and you can automate it, right? You can use AI and ML and deep learning and all this
How long
buzzwords,
does it take?
which unlock funding.
For curiosity, like how long does it take to scan one phone and compare it to blueprints or something?
But you can, that's a good thing. You can separate that, right? You can do the data generation, and that needs to be fast, factory line kind of thing. And that's, I don't know, a couple of minutes. It doesn't take, and you take not only one, you take many different, there's jigs and these kind of things. And there are devices made for that. That's a good thing. A lot of the things we learned is you can use quality and other supply chain aspects to tackle that and use the tools and convert them. But that's why I think there's a lot of low-hanging fruit, because tools exist. You just need to apply them in different contexts. And for example, all these 3D X-ray machines, when I spoke to the manufacturers, they were all scanning BMW parts and for cracks, and compared them automatically against the specs. I said, this is exactly what we need, right? We want to have a 3D model of what we have, and then we want to compare it, and it should automatically show red, green, the differences. All this exists. So that's why this 3D X-ray thing, then you get your photos, and you can apply all kind of software afterwards. You can continuously improve the algorithms. You can tap into all the AI community, pattern recognition, and you can do your own stuff. And then you can offload it and buy a couple of high-performance computing clusters to do it faster or whatever. So that's why this is promising. Yeah.
So are there any further questions? Then if there are no further questions, let's thank Axel again for this very interesting and engaging talk.
Thank you.
Thanks a lot. And now we will have a break, and then at 3 p.m. the next session will start. Thank you.
Okay. Hi everybody. Welcome to the last session of this CARDIS. Welcome to the side channel session attacks. Side channel attack session. We'll have 4 talks about side channels, and the first talk will be given by Vipul Arora. The floor is yours.
Yep. Thank you, Oliver. So the paper I'm going to present is called A Tale of Two Boards on the influence of microarchitecture on side channel leakage. So the research question that we answer with this paper is that given a choice between 2 implementations of the same core, how significant is the difference in side channel leakages? And the question we asked is something that is relevant to an embedded system engineer or a system designer who is making a crypto implementation, since we would want to determine that how is the choice of hardware influencing the side channel leakages. And it is a really common phenomena during development that we can use available crypto libraries and just use them in the project, but the hardware plays a big role. And to answer the question, we had the same software crypto implementation that was flashed on 2 different devices made by different manufacturers, but they had the same core, and power traces were acquired, which were then analyzed for leakage. So microarchitecture and instruction set architecture. So for this research, we focused on Cortex M0, which is the microarchitecture, which is based on ARM v6, that is the instruction set architecture. So a software, when compiled, is done specific to the microprocessor it is being built for. And on compilation, the software is broken down into assembly, which is basically step-by-step operations from the instruction set architecture. And the ISA basically represents an abstraction, or like provides an interface to interact with the underlying hardware implementation, that is the microarchitecture. And different processors may support the same instruction set architecture, but may have a different microarchitecture. Side channel leakages. So this has the main topic of the current session. So side channel. Side channel is when we are basically obtaining information about operation of a system without directly interacting with it. And leakages. So if we can deduce some useful information from the side channel information that we acquired, we will classify that information to be as leaks. And side channel leakages could be of different forms, but mostly we focus on power and EM these days. For this work, we used power side channel. The target devices that we used for this work were STM320F0 Discovery board, which was used, which is powered by STM32, and NRF51 development kit was used. And for the remaining of the presentation, I will be referring to STM32 as STM and NRF51 as NRF. So both the boards, targets are having Cortex M0, which is built upon ARM v6 architecture. STM32 was configured to run at 16 megahertz. NRF51 is set to operate at 16 megahertz. So I wanted to configure both the devices in the same manner in order to have a valid and a fair comparison for leakages. So they both were made to operate at the same frequency. And for measurement of power traces, a Picoscope 3000 was used. We had almost similar setup for both, but NRF51 is a low power device, so it was operating at a low, it uses a really low current of 2 milliamps. So I had to use a low noise amplifier in the setup. And the current probe was used by making a tap on the power line for the socks. And yeah, in NRF 51, we have the specific port to measure the power consumption. And in case of STM32, we made some hardware modifications and we made a tap in order to get a better clarity of traces. And in case of NRF 51, no hardware modifications were made. So the software implementation used was a tiny AES implementation, a tiny AES C library, which I got from GitHub, and it was unprotected, which was used in ECB mode. So I was expecting to find leaks, and that was the purpose of this work, so that we can compare how would the same implementation leak in two different devices with the same code. 16-byte key and input was used. So we get a 16-byte output cipher output, and ARM compiler 5 was used. Mu IDE, Keel Mu Microvision was the IDE that was used for compiling, and the same binary was then flashed for both the devices. So in this picture, you can see this is the complete raw traces that were acquired from the two boards. STM on top and then 51 at the bottom. We can see all the 10 rounds of AES and for both, and even we can see the repeating patterns relating to add round, sub byte, shift row, and mix column. So for the purpose of this work, we focused on S-box operation for round 1, marked by the arrow, and for the remaining of the presentation, the power traces which would be shown would be relating to this section. Okay, so before I move ahead, I wanted to explain the evaluation methodology we used. So key rank analysis was one of the ways where how we were determining the intensity of leaks. And in this picture, we can see, so if this is a raw trace, below this, we have the results of key rank analysis. So we select a leakage model, which could be Hamming weight or bitwise. Then we selected the target intermediate. So for this research, we had S-box in, XOR, S-box out. And in this plot, what we see here is the probability of the correct key byte being identified. So in the x-axis, we have the time samples, and in the y-axis, we have the 16 key bytes. And what you can see here is like a different, this is the color scale. So the red color denotes a high intensity of leak. That means the correct key byte would be ranked 1 or like highly. And as we go towards the colder spectrum, the key byte is not identified. This screenshot is taken from Riskier Inspector 2019. And so this is the confidence evolution plot. So for the red region, this is what we will be observing. So the correct key byte was ranked 1 in about 100 traces at the regions where it's dark red. And as you move towards orange, so I think this is the part which was supposed to be somewhere here. So it takes a few thousand traces before the correct key byte is ranked highly. And over here, we can see the results. So in this raw trace, you can see the 4 S-box operations are happening in this raw trace. So we can see that the first byte of the key is found to be leaking for this round, and like you can see the same repeating pattern. And this is where the second key byte leaks. This is where the third key byte leaks, 4th, 5th, 6th, and so on. It goes ahead. So this is the result of doing known key analysis on both on the complete trace of first round, and we can see all the 16 key bytes are found to be leaking at the respective locations. The traces were in sync, and but yeah, you can something that we can observe here is that STM32, we see that okay, key bytes are leaking at the regions where we would expect them, and in case of NRF51, we see quite a lot of red, but it was pointed out to me at a later stage that I did not remove a coupling capacitor on the power line. So I think it could have had played a role, and we are seeing a diffuse effect of leakages for NRF51 results. And in order to, the part of my research was that I wanted to do instruction level modeling. And for that, I used Keel 5 ARM simulator, and I did the disassembly of the C code we had. And the Keel ARM 5 simulator was used to obtain cycle accurate timing information. So we had the store instruction can take more than 1 clock cycle, or it can take up to 2 or 3 clock cycle, but all that was handled by the ARM simulator. And then this data was exported, and a Python script was used to link this data to the power traces we had acquired. And this is how the power traces look after they were labeled. And in this slide, we are having the power traces from STM board on the top, NRF at the bottom. Instruction labels are added here. Load show, which you can see are considerably longer, branch instructions. So this is some things that you can observe just by looking. And another observation that we can make is that the trace sets which I had were fixed versus random, and they for these plots, the mean was calculated of all the fixed trace sets as well, and the fixed trace sets are plotted in blue, and the random trace sets, the mean of random trace sets is plotted in red. And something that we observe is that there are specific sections of the trace where we see that red plots and the blue plots start deviating from each other, and this already implies that there might be some dependency on the data at those sections of the trace. So for this research, I acquired multiple data sets. So I had 2 classes, STM, NRF. For each device, STM, I had 2 boards, board A, board B, because I wanted to evaluate for interboard variations, which I was hoping to find some information relating to manufacturing defects. So that's something that I wanted to check with interboard data sets. And then we had multiple data sets from the same board, which are an intra-board. So we had sets which had the data, input data, the fixed input data was changed between D1, D2. And then there were inter-key data sets with key 1, key 2. So in total, we had class, board, key, data, repetition, 5 parameters. Each parameter could have 2 values, 2 to the power 5, 32 trace sets are all specified here. Fixed set 1, fixed set 2, and board A, board B, key 1, yeah. So in this slide, I show the statistical analysis of power traces. Yeah, so this is the plot of means of fixed sets and the random sets for STM on top, NRF device, NRF on the bottom. This is same as the previous slide, but we can see that the deviation is here. And below that, we have the standard deviation plot for the trace sets. And we can observe that, okay, the standard deviation plot for fixed sets is plotted in blue and random sets is plotted in red. And we see that fixed sets have a repeating behavior every clock cycle. And the random, so yeah, and in case of random sets, that we can see that the behavior can vary at certain locations. Like we see here that the standard deviation increases for the random set significantly over here, but for fixed sets, we are mostly seeing a cyclic behavior, which is repeating, yeah. And so on this slide, we have the analysis of SGM board. The board A results are plotted in red, board B results are plotted in blue. And in all the previous plots, we were having like actually 4 plots. So we had dotted lines. So for TVLA, we have to perform every experiment twice in order to show that those results are not incidental. And what we see here is, yeah, TVLA relating to different instructions has been plotted here. The threshold is shown by the green line. It is not clearly visible here. And below that, we have the results of key rank analysis on board A, board B. We see that the key rank analysis results are almost same for both the board iterations. So I was hoping to see effects of manufacturing variations in these results, but unfortunately, I did not find something significant. Yeah, and we can see that even the TVLA results from the both boards are almost identical. But something that we see here is, which is shown by the red square, is that even though TVLA threshold has not been crossed on applying DPA and like the known key analysis results, we were able to break the correct key bytes, even though the TVLA threshold was not crossed. And this was applied on a trace set with 1.25K, 1250K traces, yeah. So these are the results from NRF board. And we again see identical behavior from both the boards. We see a minor drift between the red and the blue plot, but that is something that I think was like because of unsynchronization between the two devices, and that is incidental. But between the device, we don't see a lot of deviation between the solid red line and the dotted red line, neither the solid blue line or the dotted blue line. And we see a similar behavior of false TVLA false positive at the red square, that TVLA says that there should be no leaks, but we were able to find the correct key byte to be leaking in this region. And at the same point, TVLA in the region marked by the blue square, we found that even though TVLA threshold is exceeded, we were not able to find the correct key byte. But I think this is something that relates to the model that we were targeting, and information is leaking there. That is the reason that we have a TVLA peak, which is based upon distance of means and standard deviation. So there is a dependency on underlying data, but the model might need to be changed, or yeah. And in this slide, I present the overview of TVLA results for an NRF device at the bottom, SGM device on the top. And we can see that we find leaks at the similar locations, but different the same instructions can be found to leak differently on two devices, and there can be a lot of reasons. We were not able to pinpoint. We cannot pinpoint them exactly, as the microarchitecture is not available publicly. But since NRF device is a low power electronic device, there could be decisions that were made during the manufacturing, or like specific manufacturers can make decisions that have an impact on how specific instructions can leak. So summary of the presentation is that I went over the methodology to compare performance of devices executing the same software implementation, how we can understand the TVLA results and have their relationship to the leaks. And we compare the performance between to hardware iteration of the same core. Yeah, with that, I close my presentation and I'm open for questions.
Thanks for the talk. So thanks for the talk. Is there any question in the audience? I see there is one over there.
Thanks for the nice presentation. Yeah, at some point you say that in the NRF device you had a capacitor that maybe were diffusing all the leakage. Have you tried to decouple that capacitor and acquire and compare it to the other target?
Actually, no, I didn't do that because this was something that was pointed out to me when I submitted this paper, and I did this work quite a while ago, and I didn't.
So
but I am curious, and I would want to do that at some point.
Okay, thank you.
There is another question there.
Hi, thanks for the presentation. I was wondering, could you elaborate maybe again on how you map the traces to the specific instructions?
So how I mapped the traces to specific instructions was basically the reason I chose Keel IDE was that it had an ARM simulator. So if you create the disassembly, there is a possibility that you can use the simulator. It has an inbuilt simulator, and with that simulator you get this sort of output where it tells like which instruction is executed at which timing. So I chose the target instruction where I was entering when I was entering the interrupt function. I noted the timestamp of it, and then in the Python script I just subtracted that to get the relative to get the relative time from the absolute time, and then that absolute time was exported to a Excel. Then I knew the sampling rate of the power traces, so I knew the timing information, and then that previous timing information was used to link the instructions to the power traces.
Thanks. And that timing information generated by the simulator, right? Does that take into account, say, pipelining effects, stuff like that? It does. Yeah. All right. Thanks.
So and this you can also see for the load instructions, it's 2 clock cycles, branch is 3. So I was surprised to find that yeah, like it was doing a complete accurate cycle accurate simulation, and I even verified this. So I don't have the picture here maybe of the complete trace, but when I compared the multiple the power trace from multiple S-box operations, I was finding a similar shape. We have a peak here, then a valley, which was relating to the same instructions at each location. So that also increased my confidence that the traces were in sync.
All right, thanks.
Okay, thank you very much. I see that there is no other questions, so we can thank the speaker again. Okay, so the next talk is about measurement setups and how to compare them efficiently. And the talk will be given by Balázs Udvareli. Balázs, are you ready? So the floor is yours.
Okay, thank you very much. So this is the title of this work is Towards a Better Understanding of Side Channel Analysis Measurement Setups. And I did this work with David Ebelitia and François-Xavier Standard. So as an let's say you have an implementation, and you want to evaluate its security. And you want to be in the green zone when this is what you consider secure for yourself or for your product. And you measure and make some attacks, then you observe that you need X traces to attack your implementation, and you consider this secure. Okay, that's nice. You give it to your colleague, he does experiments too, and he observes that he needs even more traces. But this is not the whole story. There could be somebody else in the world having a much better measurement setup, and who gets to attack your implementation in fewer traces that you consider not secure. And this is the problem of side channel measurement setups, is that they are prone to security overstatement, and noisy setups, they lead to a false sense of security, which we don't want. And basically you could be anywhere on this curve. And if you have noise amplification countermeasures like masking or shuffling, it's even worse. You could be on the red curve, and we see that the curve is much steeper. And so side channel setups are frequently mentioned in the papers, but they are not many systematic studies. So this is why we propose to analyze 4 parameters of side channel setup. And this was done over 2 platforms, a hardware one and a software one. So our measurement setup is a very classical one. You have the device under test here, which will be an MCU or an FPGA, and this is the power supply, and we sense the current that is going through to the powering of the chip, and then we amplify the signal or not. And we match its impedance, and we sample it with an oscilloscope. And we use a trigger signal from the device under test to synchronize our measurements. So here we see that we tested the probing method. We tested the clock frequency of the device, its power supply value, and the sampling rate of the oscilloscope. So a bit more in detail. We used two probes. We used an inductive probe, which was a Tektronix CT1, and a shunt resistor. And for the amplifier, we used an amplifier that provided 20 dB of gain. And for the clock speed, we tried to have a broad range of clock speeds. For the supply voltage, we used the minimal, the nominal, and the maximal value of the chips. And for the sampling rate, we choose to sample relative to the clock frequency at 1, 5, or 25 times the clock frequency. So this is a total of 108 cases for each setup to analyze. And I will have a quick word on the targets that we chose. For the hardware platform, we used a Spartan 6 FPGA. Mounted on a Sakura G board, and it runs an AES with a 32-bit architecture. For the software platform, we use the same as in the previous paper, Cortex M0 CPU on a STM32 Discovery board, and the tiny AES with a table lookup S-box. And for this board, we removed the decoupling capacitors, and we added an external crystal to have more synchronized clock. So we performed univariate and multivariate analysis of of every case here. For the univariate analysis, we based ourselves on the SNR, and because the SNR is an approximation of the attack complexity of a univariate attack. And we can see here the SNR for the hardware platform and the SNR of the software platform. We see that we have a way higher SNR in the software case. We reach values of almost 3. And we also see that we have one set of peaks here in the close vicinity, so in the same cycles. And in the case of the software, we see that we have multiple peaks that are separated by many cycles. So this is our results for every set of parameter for the hardware case. And how to read this graph. So basically, you have a bunch of numbers in log scale for the SNR. And I'm not sure that you can see it from behind. So basically, look at the color. The darker means a higher SNR. So we have the best case, which is situated here. It was observed with the CT1 and with the amplifier. We observed that the highest sampling rate was the best. And our results show that if you sample at only once the clock speed, 1 times the clock speed, then you get way worse results. Same for the DUT clock speed. We see that we reach very low values of SNR if we have a high clock speed. And for the DVDD, the difference is smaller, but still we had better results with the lowest VDD that we were able to achieve. For the software case, here is the best case that we observed. We see that this time we had the best case with the resistor and not the CT1, and still with the amplifier. Same thing for the sampling speed. You must sample at a higher speed than once the clock frequency. And this time for the clock we had a different conclusion. We observed that the best case was observed with the highest clock, so with 48 megahertz. And again, same thing, the lowest VDD was the best. For our multivariate analysis, we know that multivariate attacks exist, and but we want a simple multivariate metric, and we chose to use the perceived information, so the PI. To do this, so the PI is actually a lower bound of the mutual information. And to do this, we profiled Gaussian templates, multivariate Gaussian templates in the principal subspace for all the setups. And so we estimated the mean vector, the covariance matrix, and the matrix W. And the matrix W was estimated with the linear discriminant analysis, so LDA. And we chose LDA because it maximizes the SNR in the subspace. We used in the row traces, we used up to 500 samples, and we used up to 50 dimensions for the output dimensions of the LDA. So basically, we did multiple profilings of for each setup case. We performed multiple output dimensions number. So we profiled. We had many templates, and we chose the best one that gave the highest PI value that I will show on the next graph. And just the last element here is that the PI was chosen because it's directly linked to the complexity of a multivariate attack, and which is based on the estimated model that we estimated. So here are the results for the hardware setup. We see it's still in log scale. If you see the minus infinity value, it just means that the PI is actually below 0. So there was no usable information that you could extract from this setup. And so this is the plot of the highest PI value for each case. And we observed that the best case, the highest PI value, was obtained with in the same case as the SNR. For the software platform, it's again the same. Just as I note, the PI, the maximum PI value that we were able to extract was 7.96 bits out of 8 bits of profile value. So it's almost the complete variable that is extracted. And we see that there is generally higher amount of leakage that we could extract with the software platform. And also, if you see, there is very high amount of dark blue. So the sensitivity to the setup is way lower. So now I will discuss just setup parameter independently. So the question about the probe, we saw that it was more critical in the hardware platform, and the inductive probe, the CT1, was the best choice, and most probably it was because it is just a coil, so there is no resistive element, so it must be less noisy. For the software leakage, they were way easier to exploit, and they are less sensitive to probes. And in the software case, the amplifier did not have a significant impact because the signal that we obtained was in the vertical range of our oscilloscope, so we basically did not have to amplify. But the amplifier could have advantages if you attack more advanced technologies with the smaller nanometer scales, or you use signals that are coming from lower signal probes like electromagnetical probes. For the clock speed of the DUT, this is the conclusion that we would say, like a take-home message. So use the highest available clock frequency such that independent clock cycles are easily distinguishable. So why is this? If you see here, I extracted the traces of the hardware hardware platform for various clock frequencies. We have the 1 MHz, the 6 MHz, and the 24 MHz here for the full encryption. So you see the same amount of cycles here, but you see that here you can clearly distinguish the independent clock peaks. Here it's more or less distinguishable. Here, well, you see no clear peak at all, and you see that the PI here and here is quite okay. It's quite high, but here it's below 0. So thanks to the hardware platform, we were able to conclude that you need to be able to observe these independent clock cycles. For the software case, we saw the independent clock cycles even with the highest frequency. So there was another explanation. If you sample the same amount of samples per clock cycle, so let's say 10, if the clock speed is faster, actually the interesting part of the leakage is the peak. It is where you have the rising edge of the clock and the triggers or the registers. Then if your clock speed is faster, the amount of the width of this peak is larger, so you have better chance to have more samples in this zone than if you have a lower clock speed. So this is why you should increase the clock speed if you sample at a fixed amount of sample per clock cycles. For the supply voltage, you can reduce below the nominal value of the chip, but you will not get significant gains from it. So it's because if you have a lower supply voltage, then you have a longer critical path in the MCU, and basically it spreads out the information for over multiple samples, and this has an impact on mostly multivariate attacks, and you can expect better results with multivariate attacks for this. And the possible explanation for this in CMOS designs is if you lower the power supply, you reduce the transconductance of the transistors, and so basically you reduce the signal, but you reduce even more the noise. But this cannot go to VDD equals 0, because if you decrease the VDD, then actually you have a higher resistance in the transistors, and this increases the noise. So there's an optimal value of VDD that can be found, but it was below the minimal value that was suitable for our devices. For the sampling rate, So you should respect the Nyquist criterion. So we saw that if we sample only one sample per clock cycle, then we have way worse results. And if you sample above that, then we can observe that there is no significant gain. There is always a gain, but not much. And this is probably because you have correlated samples. So you have samples that behave very similarly. And finally, univariate versus multivariate analysis. So we saw that in the hardware case, we have one single peak or peaks that are very close to each other. And then DSNR is a relatively good approximation for the attack complexity. But if you have multiple peaks, this suggests that the leakages are independent, and multivariate attacks should be way more powerful. So this is typically the case of the software platform, and there you should use the PI and not DSNR. So small conclusions here. So the design of the side channel attack measurement setups is very large, and you can optimize every setup for every case study, but it's very expensive. So here we showed a certain number of systematic patterns that you can exploit, and many of them were already present in separate works. And the most important is that a bad setup can cause an information reduction by a factor of more than 10. So thank you very much. And you can have questions.
So thanks for the talk. Is there any question in the audience? Okay, there's a question over there.
When you say you need to obey Nyquist, what is the upper frequency? Because the clock frequency is not the highest frequency that you get out. Do you look with a spectrum analyzer actually at the band up to 10 gigahertz, and do you choose a cutoff there, or do you insert a low pass filter in your oscilloscope path to obey Nyquist?
We did not insert any filters. So basically, what could be the useful signal that you could exploit, you can see it if you sample high enough. Then let's say we sample at 25 samples per second. If we improve more, let's go say to 50. If we see no gains, that means that probably all the information, useful information, was in that range. But I cannot say it's what is the maximal frequency that you should choose, because it's like the internals of the switching speeds of the transistor themselves, I think, and that should be tested experimentally.
And a second question: was your CPU clock and the oscilloscope sampling clock synchronized? Yeah. These were independent.
Yeah.
So there's a bit of a lottery going on each time where you actually hit the clock.
Actually, I forgot to mention, there's an approximation site, so it's close to 1, 5, and 25 times the clock frequency, but not exactly, and no direct multiple of.
Okay.
Another question? So there is one in the front.
So I think if I understood correctly, in this software platform, when we look at this graph, you're saying that it is better to actually run the CPU at a higher frequency, right?
Yeah.
This one, because your intuition is that the more interesting observation is happening right after the rising edge of the clock cycle, right?
Yeah.
Because if you run the platform slower, you just get quite a large time where the signals are already stable inside the CPU. Is my intuition correct?
Yeah.
And then this is not really the same for the FPGA implementation. Do you have an intuition why it's not the same?
It's not the same because here you see that the clock the power trace, like it gets really smoothed out. Mostly, probably because there are some internal capacitors in the FPGA that smooths them out. And yeah, you should use a high clock frequency up to the point that you still able to distinguish the independent clock peaks.
So here the peaks that we see, they belong to different clock cycles?
Yep.
Thank you.
Pleasure.
Is there another question? On the online chat? No? Okay, so I think we can... there is another one.
Am I right in guessing from these plots that this is AC coupled in the oscilloscope?
Yes.
So you get quite a lot of drift, as in the clock peaks, they build up, but your reference signal is sort of drifting up a while. And if you do template attacks, you will see the problem that your templates later on depend quite a lot on what happened earlier. Because you get all this history. The AC coupling is a high-pass filter. It has an impulse response. So you introduce a lot of memory into the analog side.
Yeah, it's absolutely true. But just that if you repeat the same process again and again, you introduce the same effect for each trace. If you see that actually in this figure you have many power traces stacked above each other, and you see that the difference between them is it's only mostly the side channel information, and no, it's not the drift that comes from the AC coupling.
But even in your first plot, you can see, in principle, if the clock frequency is long enough that the circuitry settles down, it goes to a sort of brief DC period before it starts again. But you actually see it doesn't settle down, it drifts. It's continuously going downwards in the first plot. And that's also where some memory is building up. Because AC coupling means the long-term average of your signal has to be 0, but you have all these peaks. So the oscilloscope has to subtract an offset to keep the long-term average. And that makes everything depend on each other. And then with templates, everything shifts away. Your means become less useful. So that's what I find for template attacks. It makes quite a difference whether you AC or DC couple.
Mm-hmm. But I mean, if you run the same experiment, like to get a power trace, you run the same way and the same manner repeatedly, you get the same drift for each trace. And so
you may see noise from previous clock cycles. Previous clock cycles show up as noise to later clock cycles, what the modem people call intersymbol interference.
I suggest that you get that offline, so that I mean this appears to be a long discussion. So we'll take that. It's okay, so we can thank the speaker again. Okay, so the third presentation of this session is entitled Profile Sidechain Analysis in the Efficient Attacker Framework. And the talk will be given by Guillaume Perrin. The floor is yours.
Thank you, Olivier. Hi, everybody. So thank you for attending this presentation. So this work, I'm Guilherme from Delft University, and this work, I'm co-author of this paper, which is done together with Professor Stepan, Annelie, and Sylvain Guillet. So in this framework, although we have some practical results, also experiments in this paper, this work proposes more a theoretical discussion on the side of profiling attacks and how the newly deep learning-based side channel analysis fit into attackers' assumptions, and also evaluations in how the hyperparameter tuning affect, in the end, the assumptions and the conclusions that we have made for profiling side channel analysis. So just a bit of context, we know that profiling attacks allow us to define the worst case to explore worst case security, because we can assume the strongest adversary. And we also know that template attacks theoretically are the strongest possible profiling model that we can achieve. And this is due, of course, to the underlying the statistical distribution of the data, and also because of the parametric nature of template attacks. But in the recent years, we have seen that deep learning, or mostly deep neural networks, they have shown some superior or competitive results compared to previous attacks. And but although results are impressive, and because deep learning in many domains has shown top results, so it's expected that the sidechain analysis also shows some advantage. But we are still scratching the surface, and there are many things we don't know, and we cannot conclude quite strongly yet on these things. So, but deep learning is very exploratory, so it's difficult to define what are the bounds of the analysis if we consider something that you can explore in many different perspectives. But of course, it offers advantage for an attacker, and mostly because we can assume that feature selection can be relaxed in with deep learning, because the neural network automatically identifies what are the main locations of the leakage. And also, but even if we have seen that many research recently, authors have used feature selection, but there are some exceptions where some attacks have been demonstrated on raw data where no feature selection was used. So we can assume this is possible. And also we can say that in convolutional neural networks, mainly although they don't eliminate misalignment, but they make the analysis less sensitive to misalignment. So the main question that we come by analyzing, by putting deep learning into profiling sidechain analysis, how exactly hyperparameter tuning will affect the adversary's assumption in profiling SCA. And we have seen that the most focus, of course, because we have many options to explore, many different techniques for hyperparameter tuning, and every month, every year, there are many research on this domain that propose new techniques, attractive techniques to try. The focus has been a lot on the hyperparameter tuning and trying new techniques, but not so we don't see at least in academia, we don't see a lot of papers comparing exactly how the number of profiling traces affect profiling attack using deep learning. We see more the comparison of how the technique, the hyperparameter part, is affecting the attack result. But also the negative side of focusing on this side is that it's difficult to understand, and it's difficult to compare, to do a fair comparison between different techniques for deep learning sidechain analysis. So how, mostly because the complete hyperparameter tuning effort is omitted from the results and omitted from the final result, let's say. We can see what was done, the conduction, but exactly how much time was taken, what is the computing power, everything, this is not really clearly demonstrated. So in this work, we have, in terms of contributions, we propose a framework where we not solve the problem, but we do a step forward into the understanding what is the minimal power for that an attacker requires to conduct a successful attack. Keep in mind that all the time I'm talking about assumptions here, I'm talking about deep learning for profiling sidechain analysis. I'm not talking about template attacks or other attacks. So we wanted to know what is the realistic assumptions we can make in this context. And yeah, so let's say the legacy sidechain attacks, or I mean, everything that came before deep learning, we say that the number of traces, the main component, although also when I say number of traces, we can include here the quality, like previous talk was showing, to estimate the power of an adversary. And also then we have, with deep learning based at SCA, we have one more component, which is then what we define in this paper as learnability, which is the scale of amount of tuning you can do from in a profiling SCA. So a bit of context on deep learning based SCA. So we are talking here about neural networks, and when we talk about neural networks, we say we need to be aware that we have many hyperparameters to define, in the sense that small modifications in the hyperparameters completely modify the profiling model results. And then most of these hyperparameters will define the size of the model, also the capacity of the model to tune, to fit the features, and also we mostly, besides the fact that there are many loss functions being proposed for sidechain analysis, category cross entropy is still used as the main one, which provides a competitive result. And the loss functions also define many other hyperparameters which are related to that, like optimizer, regularization, number of epochs to train, batch size, so all these things. So, and this is important to mention because when we define many different hyperparameters, this means that we are, how we vary the hyperparameters directly impacts in the number of experiments we are able to try. So, but to construct this framework, we need to make some assumptions on the model for the profiling model using neural networks. So we cannot just take into consideration profiling models that simply underfit. Sorry, I think I wrote that does not underfit, sir. Yeah. So it's underfitting is usually characterized by the unchanged loss function, in the sense that the data is not being fitted at all by the model. So this model needs to be discarded from the process. It cannot be taken into account. Also, we allow models that aggressively overfit, because we observe the overfit in terms of accuracy and loss. Accuracy goes to the maximum, loss goes to the minimum. I'm talking about training loss, of course. And we also need to consider the best possible metric to estimate attack generalization. And up to now, besides that, many metrics are being proposed, many others will be proposed, but guessing entropy is still what is the safest choice, and to define what is a good model in terms of generalization. But there are so many open questions, for sure. This is how to measure overfitting. Of course, we cannot quantify exactly what is overfitted just looking to metrics like accuracy and loss, because even models that overfit the data can recover the key. But these are conclusions made for specific data sets, most of them with a high signal to noise ratio. Also, from given model, the required learnability for a given problem, the required learnability is unknown, because due to the huge amount of infinite possibilities of hyperparameters, it's difficult to make a scale from the minimum bound to the maximum bound of learnability in this scenario. So this is a very simplistic illustration of what is how the dimension of learnability will affect the conclusions on the attack. Let's say profiling attacks without tuning. So I'm not saying that which belongs to the past or to the future. It's just that things are being modified if you add another dimension. But attacks, profiling attacks without any tuning process, we can say that we analyze when the test fail means the key is recovered, is when by comparing the number of traces and the number of attack traces and profiling traces. And if we add another dimension, what I wanted to show here is that even if we have increased the amount of profiling traces, and we don't ensure that the test will fail, that the security assessment is well done, because if we have a very bad learnability in this dimension, it doesn't mean anything for the number of profiling traces you are adding to the process. In other words, if you have a very bad model, it doesn't matter how much traces you add to the process. This is not the same in other profiling attacks, because we considered correctly the statistical model for your situation. So it's in terms of the state of the art for deep learning for profiling sidechain analysis, I would say that the best achievement so far that is clearly accepted is that we have successful done profiling attacks against first order masked implementations, for example AES, and this is done for different bit size software platforms and also FPGAs. we are not aware of any attack that is able also to defeat without feature selection second-order masking, for example. But we have done some good achievements in the sense that we have seen many efficient methodologies for defining good CNNs. Although these very efficient methodologies are good for specific data sets, but they are very interesting in the sense that can help defining the CNNs for different data sets that contains different specificities. So we also have seen some unifying deep learning structure. This is a very good step because then we can sort of use similar structures, relaxing a bit the tuning process for multiple data sets. And also a good achievement is that we are seeing that many hyperparameter search methods used in other different domains are also valid and well applicable to profiling sidechain analysis. So reinforcement learning, random search, Bayesian optimization, all this process show good results, and they are also this is a good milestone in the domain. But is also there is also an open questions again, which is how do we compare all these different methodologies, all these different processes when we compare profiling sidechain analysis in order to understand how, in order to see how strong is the attacker depending on the method we use. So this is why we come with efficient attacker framework, and this is a framework that integrates, very simply, it integrates hyperparameter tuning in this SCA evaluation effort or rating. And we claim that there is always a point when taking more measurements and running more experiments is more effort and the targets or the secret is worse, of course, because this framework is also restricted. And this framework also assumes that taking more measurements does not guarantee better results, because this will depend directly on the selection of the model and the hyperparameters. And also a lower amount of measurements can be always compensated by better learning. So having a stronger model makes compensates on the amount of measurements. So this is also supported by universal approximation theory. So in terms of threat model for the framework, of course, we are talking about profiling attacks. So the adversary has an open device to profile, to collect information. And we assume that this adversary can query a limited amount of profiling traces and attack traces. And this could be for many reasons, like countermeasures or evaluation restrictions. The adversary can run limited number of deep neural networks trainings. Maybe the setup that the adversary has is limited in terms of computing power, so it cannot assume an adversary that can go into infinite amount of search. And if we see why we have these assumptions, for example, if we take a look at the schemes, one of the details that the scheme pay attention is elapsed time. So we cannot consider an attack and make assumptions about the target without considering the amount of time that we will spend in the evaluation. So in short, we consider an attacker that can take the smallest number of measurements n, just put in terms of notations here, and the success that he will measure the attack is based on a specific metric by setting a threshold. And for example, the metric is guessing entropy, for example, and the threshold is when the guessing entropy is lower than 20, for example. And we assume that the attacker can be successful with the smallest number of tuning experiments, H, and the big group of experiments is H, and then each small experiment inside of this of the tuning experiments is a set of hyperparameters. So the the framework considers three components. One is quantity, which is related to the number of traces. The second is quality, which is related to the measurements. And so the measurements needs to allow for the framework to be possible. The measurements needs to allow to find the mapping between measurements, leakage, and labels. So the prediction. And it should have a sufficiently high signal-to-noise ratio, in the sense that if the measurements are determine a completely random statistic, then of course the framework is not applicable. And of course, the selection of the leakage model needs to be reasonable for the problem. And also the last dimension is learnability. So why I'm taking this plot is not a novelty to anyone. I'm not trying to define what is grid search or random search, but the idea here is to just exemplify how the selection of the hyperparameter tuning can completely affect the profiling attack and the adversary's assumption. For example, if you have grid search in a way that the best possible combination of hyperparameters rely in some specific place, it doesn't matter if you select, if you do infinite amount of experiments, if all your experiments are selecting a combination of hyperparameters that are completely out of the fitting point. So, and random search tends to determine, to skip a bit of this problem, because we never know if you ended up selecting a group of hyperparameters that is close to what is ideal. So the way, if we do an evaluation, if you want to make conclusions for your profiling sidechain analysis, but you use a completely, let's say, not good hyperparameter search process, when all your selection is no sense, so the framework also doesn't make sense, because you are selecting the dimension of the learnability will be not efficient for the case. So the final assumptions on the framework before I go into the experiments. So we also assume that the adversary then is bounded in terms of computational power and measurements. We say that the attack must be possible, but does not have to be successful, of course. And we are talking about here about supervised learning. So we assume that the profiling measurements should allow learnability about the problem, as I defined before. And we say that an attacker with more quantity, more measurement, should be able to deploy a weaker attack. This is what we should observe in this framework. Otherwise, if we have more, if we have less measurement, then we require, of course, a stronger model, which then relies on the how big is your dimension in terms of learnability. And what is not realistic, of course, is to assume somehow that the attacker is unbounded, because the attacker is always bound. So, but in a case where the attacker has a lot of measurements, learnability, and is not really bounded, then in essence you should be able to break the target with a single trace. So this is the algorithm that defines the. Okay, 2 minutes. Okay, I will speed up. I will skip the part here because I think it's not, then I go directly to the to the results. So we use it in these experiments, the ASCII dataset, which is a software implementation of AS with first order masking. And I will, yeah, so here are just the neural networks we consider for a random search in the case. But I wanted to show two results specifically that demonstrate that the number of traces when we have, so the green color means more models we try, the red color means less models we try, so less learnability. And what I wanted to demonstrate here is that for some specific models, the number of traces is less important than the amount of hyperparameter tuning you try. But of course, this is Hamming-Weight leakage model, which allows less profiling traces than compared to identity leakage model. Go to the other side. So in the other scenario here, we see that the number of traces and the number of hyperparameter experiments are important in the same sense. But I wanted to, sorry, I'm always going to the other side. But I wanted to show you also here what happens if you have a very strong adversary. And in our case here, a strong adversary means an adversary that can do a very strong model for the case. And in this scenario, we can see that the number of profiling traces when you have a strong adversary doesn't matter so much, because the number of what matters more is after some number of profiling traces, the learnability is what affects more the results. Although number of profiling traces increase the chance to make a better attack, but they don't impact so much. Okay, so just to define the result here, to not take so much time, this is when we apply the framework also in a realistic scenario. This is a hardware AS implementation from a real device, IoT device. where it has first order masking and a very noisy data set. And then we also observed here that how the framework, having this perspective on the framework about the number of models can really determine for us how we can increase the power of the adversary related to this target. And just to mention that in this case, we measured up to 10 million traces in this model. And just to conclude then, if model is efficient, provides low learnability, and traces are maximized, I mean use all the traces during profiling phases, then we can have a very limited view of which component has a significant impact on the attack performance. So also it's important to mention that in deep learning, the model is important, the hyperparameter is important. So if you select a wrong model or if your model is not really well defined, you are completely wrong about the estimation of the security of the target. Yeah, so in this framework, it represents how the attacks components fit into the context of deep learning for profile sidechain analysis. Okay, so then I finish my presentation, and thank you for listening. If you have any questions, I'll be happy to take. Otherwise, I'll leave my email here if you have questions for later.
Thanks for the talk. Is there any question in the audience? And we have time for one question, I guess. No? Is there one online? So maybe I have a quick one. With your framework, what do you do if your attack if you don't find an attack that succeeds? Mm-hmm. So what do you conclude? Is machine learning going wrong? Is the implementation too strong? Or?
Yeah, so this is yeah. I don't know if I can answer these questions properly, because this always depends for sure how reasonable is the process of the deep learning definition, right? So if you select hyperparameters that are not really not good for the problem, for sure you end up with anything that indicates what you have. So then you don't know which direction you go. But I would say that in this, sorry, I don't have the slide here anymore. But in the slides that I showed the real target, a harder AS, I was seeing this problem when I had the 2 million traces in the profiling phase. I was not seeing any evolution. Then I was increasing the number of models. Then I would say, okay, the number of models makes sense, so I'm in a good direction. And then I realized also number of models were more important than increasing the number of profiling traces in that case.
Okay, thanks. So let's thank the speaker again. So the next talk is about single trace fragment template attack on 32-bit implementation of Ketchak. Let's prepare the slide. And the talk will be given by Shi-Chum Yu. The floor is yours.
Okay, so I'm Shi-Chum Yu, and I will present our paper, Single Trace Fragment Template Attack on a 32-bit Implementation of Ketchak. Okay, so we believe that our contributions are as following. Firstly, we use a technique we later call fragment templates for full state predictions that will be used to deal with some very long intermediate values, such as 32-bit words. And then we use this strategy to attack a Ketchak permutation on a 32-bit device, and by single traces and with the help of belief propagation. And after we can recover the input and output of single permutations of a Ketchak, we can reconstruct the arbitrary input of SHA-3 functions in SHA-3 family. Oh, let me take some time to talk about SHA-3. And so first start from the Ketchak F permutation. It is a sequence of 5 steps, theta, low, pi, chi, and iota, and will iterate 24 times on a 1600 bit state, and it is usually described as a three-dimensional structure. So that's in the three-dimensional structure will be look like. And just remember that such state will be stored in 50 32-bit words if we just implement the SHA-3 on a 32-bit device. So with the K-check permutation, another type of function we call the K-check sponge functions that will consist of like multiple invocations of the K-check permutation. And for the input and output of the K-check permutation here can be separated into two parts. The first part that here we call the rate. That is the part will be XOR with a fragment of the input in the absorbing stage, and then the value will be taken as the output in the squeezing stage of the sponge function. And the other part we call capacity, and the capacity part will remain unchanged between two consecutive permutations. So it means like the output of the previous permutation will be directly sent to the next one. So basically the SHA-3 families are the sponge functions with different sizes of rate and capacity. So there are two papers about doing some single trace template attack on SHA-3. The first one is our previous paper. We focus on an AB device, and our sidechain node information is full state probability table. That means that our templates can give each candidate a probability. So that like all the intermediate bytes, all the candidates in intermediate bytes will receive a probability. So this kind of sidechain node information is quite informative, so that we can later only use a very simple enumeration to find out the correct input and output of K-check permutation, so that we can recover the SHA-3 input. And the other one is published by Convisha et al., and they use the belief propagation, and their structure is very successful, so that even like a sidechain node information like a Hamming wave, it's not very informative, but they can still successfully recover the input of the K-check permutation. But there's a question is that the situation in 32-bit implementation is not yet very clear, that in their work, that it can only success under some limited situations. And they also mentioned that maybe like a Hamming wave is better too little information. So if we want to go further on the attack on a 32-bit device, maybe we should think about to combine the better part of both of these two previous work together. So that's like we can use a more powerful search method. It's a belief propagation on a more informative model of sidechain node. That is the full state probability table. So that's the strategy we will use later. That the strategy can be separated into the following part. The first one is that we will do a full state prediction. That means that we need to build the template that can provide a probability table for all the candidates for the intermediate values. And then we will marginalize the tables into binary tables. So that now, like for the intermediate values, like each bit, we will have the probability of if it is equal to 1 or equal to 0. And so that we can send such information into a bitwise belief propagation for single catch-up permutation. And so it will, and this belief propagation, we will also take the capacitive part of the input into consideration, because we can always get the capacitive part from the last, from the previous permutation. So that later, but after we reconstruct the input and output of the catch-up permutation, we can just XOR the array part to find out the boundary function input. But so there's another question remain here, is that how can we build a template for state prediction on 32-bit word? So that's our main problem. So let me talk about our fragment template. So our template is a linear discriminant analysis-based template, which means that we will first project our traces onto a subspace where that the SNR is maximized, so that we can ensure the template will have a higher quality. So, and then how to project this, how to do the projection is that we will need like two matrices. The first one is called interclass scatter, represents the signal, and the other called total intra-class scatter represents the noise. So that these two matrices can be determined by the profiling trace as well as the traces corresponding intermediate values. And then we will use the probability density function as the prediction on such probability tables. So the problem here is that if we want to directly build the templates on 32-bit words, it will be impractical, because like I guess here no one will want to compare all the 2 to the 32 templates. So our method is that we will cut them into fragments and target on one fragment each time. That means that if we directly build the templates, we will use the LDA projections to project the traces onto maybe a subspace with maybe higher dimensions. But now if we cut the 32-bit intermediate values into maybe 4 bytes, and then the matrix, the two matrices we use to project, the value will change, so that we can project the same trace onto 4 different subspace, where that for each subspace we can only focus on the corresponding fragment. So let me use maybe easier example to explain more. That is, now assume we target a 2-bit secret, and with the value of both variables used in the LDA projection, the trace will be projected onto the following subspace. So it's maybe a 2-dimensional subspace. And now, now if we only look at the 1 bit, and we just and here the 2 matrices we use to project will change, which means that now the other bit we didn't look at will be treated like a noise. So now they will project it onto a lower dimension subspace, where that we will focus only on how to distinguish the value from the first bit. And so that if we only look at the first bit, it should be projected to the direction with the blue arrow. And while if we only look at the second bit, it will project it to the direction the same with the red one. So because I already introduced how to build the template, let me talk about inside K-chart permutations, what are the important states we need to target at. In this part, because we reuse the factor graph of K-chart made by Confucia et al. So basically, we will target on the same state, but the only difference here is that we use different way to denote the variables. So like, because some function inside ketchup can be reduced, so we only need to choose either alpha over alpha prime state here to send into the belief propagation. And also like we only need to choose either beta or beta prime. And then because Confucia et al., they just separate the most complicated state theta into 3 subfunctions. So it means that there will be some additional nodes for variable nodes inside the graph. So that's to represent it some parity inside this function. So we will also target on these additional variables, so that because we just saw that to some it will more or less provide some more information. So that will be how the graph looks like at the state level. So let's talk about how we did our experiment. So that's our target vote. We just write the official C code of K-check onto Chip Whisper Lite 32-bit version board. And although there are an onboard oscilloscope called OpenADC, but it may be not suitable for our tech because like we expected that the trace will be super long. So we need an external solution. So we use the external oscilloscope as well as some wave generator to make sure that all the systems are still phase locked. And also because now we use an external oscilloscope, it means that there is a transmission line here. So we need to also do some small circuits on the connector, so to make sure that there will not have any impedance mismatching issue. So yeah, it should be, because like template are very sensitive, so we should make sure the quality of the template are still good. So that's the platform look like. So because our row trace is still too long for building template, we still reuse the R-square technique we used previously to detect the interesting clock cycle. And also we resampling down the row traces so that the trace will be shorter. And we record like 64,000 profiling traces and 1,000 validation traces to estimate the template quality. So, and we estimate by like 2 ways. The first one is we call success rate, is that the ratio that the correct candidate got the highest probability prediction. And the other one we call the guessing entropy, which is the ranking of the candidate. So, but I'm sorry about the numbers. Looks very small, but like so. But you can find it on our paper. So I just gave you the small conclusion here is that our recovery on the alpha prime state is most successful because we detected more clock cycles, more interesting clock cycles here. But like the probability table that we obtained still can contribute information in later belief propagation. So later, because we will marginalize the table into binary tables. So that's the result after we marginalize it. So we can see that even before we send the probability into belief propagation, in some states, like in alpha states, that's already like 1,000 and more than 1,300 bits are already recovered, which is about like over 80%. And then we will send the marginalized tables into the bitwise version of the belief propagation. So there are some changes that from Convicia ADAS version. The first one is that because that's already marginalized, so we don't need a clustering technique they use to deal with the Hemingway. And some other minor changes are like the definition of an iteration here is a little different. And the order to update the tables are also a little bit different. And also there are some minor changes in the exit conditions. And then unlike their version that so far we did not use the damping technique because we found that the number they suggest may not be directly used in our version. So maybe the number still needs some fine tune, so we will leave it for some future optimization. So that's the result. We tried to use the probability tables that from 2 rounds of permutation or 3 rounds of permutation or 4 rounds permutation with like 1,000 validation traces. And because I just mentioned before, like in a spongy function that the capacity part is an unknown part. So we can also use the information from capacity part. So here, we just assume that the rate part is the size of, okay, the same with SHA-3 512. And we can see the results are very successful. So like, and if we use the 4 rounds, it will reach the 100% successful rate quicker with like a few iterations. And also we just try to set different size of rate part and capacity part. We will see that because like the SHA-3 and shake functions will only lies inside the shadow area. So it seems like if we only use the 4 rounds will be sufficient. So that's the result of like we attack on SHA-3 512. Like the successful rate is 0.1, and that's the results on all the functions. We can see like it will be most successful where the capacity part is longer. Okay, so that's our conclusion is that 32-bit SHA-3 implementation can be vulnerable to fragment template combined with belief propagation. And we hope that the fragment template technique can be extended beyond the attack on SHA-3. And because like the full state recovery by templates of a long intermediate value maybe no longer impractical. Thank you.
Thanks for the presentation. Is there a question in the audience?
Hi, I have a question. So you assume that you know the capacity part, that those bits are 0 and the rate is unknown, right?
Yes.
So in the previous paper, we found that the success probability heavily depends on what the input actually is, if it's just a short seed or if it's something longer and random. Did you have a look at that maybe? Did you find something in that direction, that the success rate depends on the input?
You mean the size of rate part or capacity?
No, if it's just, I don't know, 128-bit input. Or
Oh, I see. It's like because I will be padding, so the original size. It seems like the change will be very minor because like maybe only 2 or 3 more iterations.
Okay. Thank you.
Is there any other question?
Sorry. And I also want to say thank you that your paper inspired me very much.
Okay, so maybe I have a short question. So usually I try also to do attacks on chat-free with bait propagation. I had issue with when I was targeting 16-bit words, but then when I had to do rotations within chat-free, it made belief propagation super complex to me. And do you think it's possible to put rotations within your factor graph with larger words than a single bit?
I will say yes, it will be very time consuming. So that's the reason why we just cut them into different, cut it into bits.
You cut it into bits because of rotation or because of computational reasons?
I think maybe more about the computational things, and also we believe that the quality of our template is good enough for we can cut them into bits, we will not lose so much information.
Okay, thank you very much. No other questions? So let's thank the speaker again, and that concludes the session.
So yeah, that brings us to the closing session. So the final words for CARDIS 2021. So I just wanted to give you a short update on the participation, especially also for the on-site people. A short update on the we have a further increased number of online registered participants, but I also wanted to show you how much participation we had throughout the conference. So this is a graph. Unfortunately, the scale is not too nice here. We have, even I can see it here, between the laser pointer, right? No. There, thanks. We have around here, we have 16, and here we have 24. So we see around 20 participants, 22 up to, it peaked around 30 online participants watching the stream throughout the conference. We always had about 20 people also around online. So I thought that was maybe interesting. Yeah, and that brings us to the final words. I would like to thank all the people that were involved in making this a success. And of course, one big part of that is participants. So thank you very much for being here, both online, of course, but also here in presence, which was when we planned the event, was kind of a risk. We didn't know how many people would come. So thank you very much for being here. Then, of course, I would like to also thank the sponsors again, also there, especially Riskio, who had a booth, and Infineon, so that the bigger sponsors. And then we had Hardware.io, New AE, Rambus, Thales, and NXP, who also all supported this event financially, and in content, which was very nice. And finally, yeah, the authors, great program. Program chairs, and I would also like to thank the team that helped, the reviewers, of course, yeah, that's what I talked about. The local team that helped organizing, where there were quite a few people involved here. In particular, I would like to thank the core organization team, Tore, Timan, Ines, and Alex, and of course there were several other people from the university who helped out. In many cases, like Mr. Philip, who also provided some of the equipment and so on. So please, let's give them a hand, because they really helped making this a success. Yeah, with that, yeah, sorry. I already saw them, sorry. Yeah, with that, thank you very much, and I hope to see you at CARDIS 2022. And I will give over.
Yeah, also from our side, thanks a lot. Yeah, thanks a lot to all the authors, to the reviewers, to the session chairs, physically and virtually, to the presenters, and yeah, we are very happy. It was for me, it was the first time that I had the pleasure to be the co-chair of a conference. I certainly learned a lot. I hope that you enjoyed the conference. As we said, we will also send out a form and gather some feedback, and especially feedback on the format of the conference, on the hybrid mode. And it will be quite interesting to see how the pandemic develops, the situation, and if CARDIS next year will be a physical, a virtual, a hybrid, or maybe even something else event. And and then I think the remaining task is CARDIS has post proceedings, so we will send out some instructions how to get your papers into Springer LNCS, and then hopefully also on paper, on physical paper, and not just virtually on the website. And yeah, with this, I'm not sure, do you also want to say something?
Yes, thanks so much to invite us to Lübeck. It's a nice city, and it's a nice one to discover the city. And yes, also thanks to your team for all the work they do. It was really great. I think it's a lot of work, and really thanks.
Yeah, thanks a lot. And then I think, enjoy the remaining time, good discussions, enjoy Lübeck, and see you soon. Thank you.